hello everyone. So it's not 10 o'clock, but I want to start from the opening remarks. So this is a team workshop of the RIKEN AIP's deep learning theories. So you know that AIP, so the name of the AIP is more officially it is Center for Advanced Intelligence Project. It was founded in 2016 in RIKEN. And it was funded by Ministry of Education, Culture, Sports, Science, and Technology, the MEXT. And so nowadays, we have a lot of employees, like 137, and other many visiting researchers and internship students. So it's very, very active now. And a very special thing of this AIP center is, so this is very exceptional thing is that we have a good office here. So we have an office in the center of Tokyo, the Nihonbashi office. So yeah, this is a very exceptional compared with the other centers in RIKEN. Yeah, and there are also so many offices all over Japan. Yeah, so that means that we have a lot of researchers in AIP all over Japan. Okay, and so AIP consists of 3 groups. The first group is a generic technology group, and the second one is a goal-oriented technology group, and the third one is the AI in society group. Okay, and as you can imagine from the name, the generic technology group is working on machine learning, core machine learning technologies, and we are working on the theoretical side. Okay. And in a goal-oriented technology group, so they are working on like computer vision and NLP and AI for science. They are much more application side. Okay, in an AI in science groups, they are working on like a security and the fairness and like a privacy and that kind of things. Okay, and we are in a generic technology group, and fortunately, we could survive in this 10 years. Okay, so this is thanks to the hard work of the group members. Yeah, and yeah, so here are much more concrete examples of research topics. So actually, RIKEN AIP is working on the theory of deep learning as we are doing. Okay, and also we are developing a new methods from the theoretical side. So actually, Masashi, who is the head of this AIP, has been publishing a lot of papers on this field. Okay, and moreover, so there are AI for science, yeah, and some application to the some problems on the societies. For example, in Japan, is suffering from many natural disasters like earthquake and typhoons and so on. Actually, today is so hot, and we have a very heavy rains, so it's also a problem nowadays. Okay, and here are some a study on AI in society, like ethics, and like privacy, and security and reliability. Yeah. So yeah. So actually, so then you see that in AIP centers we are working on AI from many aspects. And we have got a lot of MOUs with many institutes in all over the world. So actually, we got 36 MOUs with the institutions in all over the world. Okay. And then accordingly, we have organized a lot of workshops from 2018 like this. Okay. So this shows that AIP Center is very active to collaborating with other institutes. Okay, so here's the publication stats from AIPs. So actually, AIP is actually the most productive institution in Japan for like AI conferences. Yeah, and so in 2024, in the NeurIPS, so AIP published 41 papers, and for the ICML, this year's ICML, so we published 29, and for the iClear, we got 29, and AI stats, so 17. Okay. The number in the brace here is the publication from our group. So we published 10 papers in NeurIPS and 10 papers in ICML and so on. So yeah, actually, maybe we can say that our team has been contributing to the AIP so much. Yeah. So yeah, we are very happy to do that. Okay, and here are more details. And here is more detailed information about our achievement from our team. Okay, and we have been invited to many international conferences, and actually, so we have been invited to some mathematical institutions in all over the world, and also we have gave some a tutorial and keynote talks in domestic conferences like NLP and the computer vision and AI conferences. And so this year in the iClear, so we have organized a Delta workshop. So that was something like this. And also, so last year, so we organized the IB's workshop, which is the biggest machine learning conference in Japan. It was like this. It was very successful. That we recorded the highest number of attendees in the history. Okay. And here is some award information. So we got the Outstanding Paper Award in iClear 2021, Atsushi and me. And so Wei Huang got the awards from KAUST 2025 Rising Star Award and CPAL Rising Star Award. Okay. And here are many other domestic awards. Okay. And so because since this AIP Center was founded in 2016, so this year is like a 10 years anniversary. So then at this period, so many teams has been organizing their kind of achievement reporting meetings, workshop like this. So this is a kind of wrap-up workshop to report their achievement in the past 10 years. Okay. So then we are following this trend, and then so this is this workshops. So yeah, so the purpose of this workshop is to give a kind of an overview of our achievement in the past 1 decade, and also we want to discuss deep learning theories in this workshop. Okay. Okay. So here is the deep learning theory team deep learning theory workshop. So this workshop, yes. So we have already seen a lot of success of deep architectures like LLM and diffusion models. So these deep foundation models are very successful, and it has a very strong impact on the societies. Okay. In the machine learning histories, the theory and the practice have been interacting to each other, so they are developing simultaneously. But nowadays, the practice is much stronger. So actually, so yeah, so practice, so like empirical research is going much advanced. But so yeah, actually, so there is a huge gap between practice and theories. But on the other hand, we want to catch up the practice, and we want to give much more insight to the practice from a theoretical point of view. So if there's no theories, then the practical research is just empirical things. So there's no foundations, just trial and error. So it's not so interesting. So as a science, we want to give more foundation to the practical success of the deep AI developments. Okay. Actually, even if we cannot give any practical insight, so the deep learning theory itself is very interesting. So actually, in the past 1 decade, the learning theory is pushing the boundaries very strongly. So through the deep learning theories. Okay? So we have seen a lot of interaction between the methodology and practice and mathematics. Yeah, actually, to tackle many problems in practice, we have developed many theoretical tools by using many mathematics. So then we see some beautiful interaction between practice and math. So then this itself is valuable. I think the development of learning theory itself is informative. Yeah. So then in this workshop, we want to discuss many interesting problems like scaling law and representations and overparameterization. And also, if we discuss our generative model, the sampling is also important, and optimization is also important topic. And also maybe through the theories, we may get some interpretabilities. Okay. So then for that purpose, so we have invited great speakers, so 9 speakers. Yes, so I'm very happy to invite these wonderful invited speakers. So we are very lucky that you could came to Japan. So thank you very much for coming to Japan. And also we have 5 talks from the organizer side. So this is our organizers, and I also want to thank the organizers for your hard work to to organize this workshop. And also, I would like to give my acknowledgement to the administrators and the secretaries. So their work is very helpful for us. So without their help, so we could not start this workshop. So thank you very much. Okay. So then now, so I want to move on my talk. So this is my talk. In my talk, I want to give some overview of the achievement from our team in the past decade. And then in the last half, I want to give some recent developments on like a test time scaling. Okay. The first half is like an overview, and the last half is more like a more topic specific. I will focus on more one specific topic. Okay, so as I said, so the deep learning has been very successful. Like we see a very huge success of generative models, like large language models and the diffusion models. But our understanding on the deep architectures are not satisfactory. So we want to give more theoretical foundation on this big success of practical applications. Okay. Yeah. So by obtaining good theories, then we want to clarify the principle of deep learning. So then we want to see what is essential to realize the good learning systems. So then we hopefully, so through this learning theory, deep learning theories, we want to go beyond the deep learning, or like we want to go beyond the current architecture, like transformers. So, but maybe it is difficult to directly find the new architectures, but hopefully we can give some good insight that could be connected to the new architectures beyond like transformers or diffusion models. Okay. So in this talk, so I will basically focus on the feature learning. So the feature learning is one of the most important aspects of the deep learning. So yes, actually, so due to the feature learning ability of deep neural networks, there are huge difference between the kernel method and deep neural networks. Okay, so the one of the most remarkable characteristics of a neural network is it has a universal approximation abilities. Okay, so it is known that a two-layer neural network can approximate any functions with any precision. This is a very known result. So back to the 18th, so there is a lot of universal approximation theories. Okay, and so actually, so one theory, so one interesting theory is a Ridgelet transform. So it gives that, so there is a kind of one-to-one correspondence between a function and the weight space. So this is an analogy to the like a Fourier transforms. So we replace the Fourier basis by one neurons. Then each neuron works each neuron works as like the Fourier basis in the Fourier transforms. Okay. Then we can transform the function f to the weight space, and then we can go back from the weight to the functions like this. So this is called the Ridgelet transform. So so then we can find a kind of one-to-one correspondence between the function and the weight space. The show will give the more detailed detailed information about the Ridgelet transform, and he will give the more recent advancement of this topic. Okay, so yeah, so universal approximability is very important. So based on this theory, so we can rely on the neural networks. So yes, so basically, if you have infinite many computation resources, the neural network can solve any problems. Okay, however, it's not actually so satisfactory because the kernel method is already a universal approximator. So what is the difference from the kernel method and the deep learning? Okay, we want to go a little bit beyond the universal approximation theories. Okay, so you know that the kernel method can be seen as a two-layer neural network with infinite widths. Okay, however, the kernel method we fix the first layers. Okay, but we only train the second layer. Okay, so then in other words, the kernel method cannot perform the feature learnings. But for the deep neural networks, we can perform the feature learnings. So this makes a difference. Okay, yes. So, so maybe you see that, so this is not so very big difference, but the ability of feature learning gives the very big difference between these two approaches. So I will give some situations where there are gaps between the non-feature learning method and the feature learning methods. Okay. So yeah, to characterize that kind of things, so we have shown that neural network has a kind of adaptivity. So adaptivity means that the deep neural network can adapt to the structure of the target functions. So there could be some unknown structure on the target functions. We want to find that structure from data. For example, maybe the true function only depends on one direction. Then we want to find such an informative direction from data. So maybe the target function has some jumps, like a discontinuous point. Then we want to find that discontinuous point from the data. Then we can show that neural network can find such a structure point. Okay. Then by doing so, the neural network can go beyond the kernel method. So there are many theories like this, and then so we can show that the neural network can avoid a kind of causal dimensionality. So by using these theories, we also gave some theories on the diffusion models and the transformers, like these foundation models. Okay, I want to give one very typical situation, the causal dimensionality. Okay, so in a typical situation of non-parametric regression problems, we have this convergence rate. Here, the S is the smoothness of the target functions, the S times differentiable, and so D is the dimensionality of the input. So this is a very typical minimax working rate, so yeah, very classic result. But you see that if dimension D is very large, then so the exponent is very small, so the rate of convergence becomes very, very slow. This is called causal dimensionality. But however, deep learning works well for the high dimensional settings, even in the image dataset. Okay? So the MNIST dataset, for example, the MNIST dataset, it's not so very large dataset, but this is already 1784 dimensionality. So if you substitute this value to here, then the rate of convergence could be very, very slow. But it works for the MNIST dataset. Yeah, so we have a kind of almost 100% classification accuracy for the MNIST dataset. So why is it? So one reason is that the intrinsic dimensionality of this data is much smaller. It could be like 13 or 14. So if this intrinsic dimensionality is coming here, then we have a much more reasonable rate of convergence. So the neural network can find this a kind of a submanifold of the support of the distribution. Then we can reduce the convergence rate. We can reduce the causal dimensionalities. Okay, so we have worked on this kind of thing in more rigorous way. Okay, so suppose that the data are distributed on around the low dimensional submanifold, and then the true function only depends on the direction along with this submanifold. Okay, so let S1 and S2 be the smoothness toward this direction. Smoothness means that how many times the target function is differentiated toward these directions. So if, for example, so that the target function is S1 times differentiable along with this line, and the target function is S2 times differentiable along with this line. But maybe the function is very smooth to the orthogonal directions to this submanifold. So maybe this direction is non-informative. So then target function, the true function is almost a constant to these directions. Then maybe the S3, the smoothness to this direction will be very large. So maybe infinitely many times differentiable to these directions. So this means that for the high dimensional settings, the target function has a different smoothness depending on the directions. Okay, maybe it only depends on a few directions, and toward other directions, the target function could be like almost constant. So we say that is an anisotropy smoothness. So in these situations, we can get this kind of rate of convergence. So there is no D. So instead of D, there is 1, and instead of S, we have an S tilde. S tilde is a kind of a reciprocal sum of the smoothness toward each directions. Here's a little bit more detailed information. This anisotropy smoothness can be formally defined by like this. This is called an anisotropy vector space. And so this is complicated more intuitively. So the norm of the anisotropy vector space is given by like this. So we sum up the SI times differentiation for each directions. Okay, and if the target function is like this, then as long as you're using the linear estimators, you suffer from the cause of the linearity. So what is the linear estimators? The linear estimator is any estimator which has these formulations. Okay, if it is linear with respect to the output yi, we say it is a linear estimators. It can be nonlinear with respect to the input x, but it should be linear with respect to the output yi. So this estimator class includes like a kernel ridge regression and a k-nearest neighbor and another Watson estimators. Okay, so because this is linear, so it doesn't have a nonlinear interaction for the choice of the features. So yeah, so maybe we can say this linear estimator cannot perform the feature learning depending on the output yi. So for this linear estimators, the worst case error is given by like this. You can see that the dimension d is coming here, so then it suffers from the Kazama dimensionality. But on the other hand, if you use the neural networks, it can find important directions. Then this exponent can be reduced to like this. So there's no d here, but instead we have a S tilde. S tilde is the inverse of the sum of the inverse of the smoothness, so Si. So let us consider very simple situations. The true function only depends on the one directions. Then it is almost constant to other directions. So in that case, S1 is small, but S2 to SD are very large. So then S tilde is almost S1. So it's not depending on the dimensionality D. So yeah, you can overcome the Kazama dimensionality. So yes, so this is a very typical situation where the deep neural network can outperform the kernel method and other linear estimators. The same thing can be applied for infinite dimensional settings. And yeah, so maybe we can consider an image data set which is almost infinite dimensional. Maybe we can consider like sounds. Sounds is also like infinite dimensional. Of course, the neural network works well for these situations. Then we can also develop a similar theories like this. Then we obtain a convergence, polynomial order convergence of the predictive error, even for the infinite dimensional settings. So if the target function has an unspecific smoothness. Yeah. More technically, so we have introduced a gamma smooth function class, and that is an infinite dimension version of the unspecific smooth function class. Yes, that is formally defined like this. So yeah, so this is like a Fourier basis. So we assume that there is only the low frequency component, and the high frequency component is there's no high frequency component for the high dimensional coordinates. So the high frequency component only appears in the low dimensional components. So then if we assume something like this, then we have this polynomial order convergence. Yes. But in these situations, if you use linear estimators, then it cannot achieve this minimax optimal rate. Yes, okay. And so what I explained is one of the very typical situations where the deep learning can be better than the kernel method. And there are also other situations where deep learning is better than the kernel method. Okay, and these theories have been developed for each individual situation, so just one-to-one. So they were not like a unified, they were not developed in like unifying manners. But we can give a kind of unifying characterizations about why the neural network can be better than the kernel method, like more generally the linear estimators. Okay, so here is the so-called convex Hull argument. This is a much more like a more unified theories. Okay, so in this theories, what we can say is that for any linear estimators, the worst case error is the same as the worst case error on the convex Hull of the target function class. Okay, so first we fix the target function class, and then we see the worst case error on this function class. Okay, then we take its convex Hull. Then the worst case error of the linear estimator is the same as for the convex Hull of this function class. So if the function class f is highly non-convex, like an unspecific smooth function class, then this convex hull could be much larger than the original function class. Then the linear estimator should suffer from the suboptimal rate. So maybe it suffers from the Casimir dimensionality. So and this convex hull argument can be applied to the all situations here. So then we can give like a unifying understanding why the neural network can be better than the kernel method. Yeah. Okay. So then, so basically this kind of theory can be derived from like an approximate theory of a neural network. So then the same technique can be applied to the other more modern architectures like diffusion models. Okay. In the diffusion models, what we should do is to estimate the score functions. Then we can use the same technique for these situations. Okay, so we give like a kind of an approximate theory for the score functions. But I should say that there is a huge gap from the previous slides and this diffusion model situations. So the analysis of diffusion model is much more involved. So we needed to more additional calculations. But so from a very high level viewpoint, so we can use almost the same technique for these situations. Then eventually, as a diffusion estimators, the diffusion model can achieve the minimax optimal rate. Okay. So yeah, so we did have this minimax rate in the ICML 2023. And another interesting property is that if the data is distributed on a d prime dimensional subspace, so the d prime could be much smaller than the ambient dimensionality. So then the rate of convergence is replaced by like this. So the d is replaced by d prime. So if the dimension of this low dimensional subspace is very small, then the rate of convergence becomes much faster. So this means that the diffusion model has a kind of adaptivity to the support of the distributions. Yeah. And also we can apply such a technique for the transformer analysis of transformers. The transformers, so transformer get an input, so transformer get a long sequence as an input, like a text. So text is very long, so it can be seen as almost an infinite dimensional object. But the transformer can work. So if you consider very naively, maybe transformers should suffer from the Casimir dimensionality, but it works very well in practice. So why is it? So one reason is that the transformer can choose the important tokens depending on the input X. So if there is an attention layer, so the attention layer can find which token is important. So then it can do a kind of a dynamic feature selection. Okay, so depending on the input X, it selects the important features, or in other words, it selects the important tokens. So through the attention layers. So because of this architecture, so that it can also achieve this rate of convergence if the target function has a kind of a gamma smooth property or something like that, and so it can avoid the Casimir dimensionality by choosing the important features through the attention layers. Okay, so this is another ICML paper. Okay, so far I haven't considered anything on optimizations, but maybe we want to consider like optimizations, and also so basically so what we have obtained is coming from the approximation errors, but there are many other challenges so in the neural networks like optimization and overparameterizations. Okay, then actually so in practice we use the overparameterized networks where the width is very large. And the number of parameters could be very large comparing with the number of data points. So, but neural network can generalize well in that situations. Why it is? Okay. The one reason is that even though the neural network is very wide, its intrinsic dimensionality would be very small. So its statistical dimensionality is very small. So we have already seen this kind of situation in a kernel method. So the kernel method is an infinite dimensional model, but it can generalize. The reason is that its statistical dimensionality is low. The same thing is also applies to neural networks. And we have obtained a kind of a compression-based bound from the kernel method viewpoint, and we have developed a kind of a compression method of neural networks. And also we have developed some optimization theory for the neural tangential kernels. Okay, so in this work, so we have obtained the outstanding paper award in ICREA 2021. And moreover, so we have developed some theories on a high-dimensional data situations, or like this. So, okay, I want to explain some of them. So this is a convergence analysis of a neural tangent kernels, okay? So if you consider very wide neural network, then the neural network can be approximated by kernel models. Okay, this is called a neural tangent kernels. So then, so if the problem is reduced to the kernel method, then we can obtain a kind of a optimization guarantees. So because everything is a kernel, so then the problem becomes a convex optimization. Then we have a optimization guarantees. So then, so we analyze the dynamics of SGD on this neural tangent kernel regimes. Then we showed that the SGD first captures low frequency component, and gradually it captures high frequency component. So if you stop, so if you do the early stoppings, then you can generalize. It doesn't overfit. Then actually we have like a minimax optimal rate like this. But so to say honestly, so this is this result is coming from the usual kernel method analysis. So yeah, this is maybe this is not very surprising. So we can easily guess, or we obtain this rate of convergence. But so we obtain a kind of approximation error epsilon m. So this term will go to 0 as the width m go to infinity. We derive this. Then so we derive this rate of convergence for neural tangent kernel regime. Then we get the outstanding paper in iClear 2021. Yes. So yeah, ATC did a very good job for this analysis. But in a neural tangent kernel regime, so we cannot capture the feature learning aspect of a neural network. Okay, so this is a neural tangent kernel regime. So suppose that we have with this m neurons, with this m two-layer neural network. If the factor in front of the summation is like 1 over square to m, so this is called a neural tangent kernel regime. So in this regime, if you go m to infinity, then this model can be approximated by some linear kernel models. But if you replace this 1 over square root m by 1 over m, then it is called a mean field regimes. In this regime, the neural network should perform feature learning, and otherwise it cannot approximate the target function well. Okay, so then we analyze these situations. So yes, so in this paper we consider like a gradient descent dynamics on the mean field regimes. So let us consider this the two-layer neural network. Okay, so you see that this is still the mean field regimes where so n is the width of the network. 1 was greater, so this is still in the neural tangent kernel regimes. So but if you take a gradient descent with large step size, okay, you do the gradient descent with very large step size. So then you can get out all the neural tangent kernel regimes. So then you will enter the mean field regimes. So actually, by taking a large step size gradient descent, we can perform a feature learnings. Then we can outperform the neural tangent kernel regimes. So, okay, so this is a small learning step. This is a small learning rate situations, and so then performance is not good. But if you take a large step size, then you can go beyond the NTK regime. So then you get smaller errors. Okay. So I should say, so this is joint work with Murat and Denny. Okay. This was a very nice collaborations. So here's the intuitive explanation why the large step size one-step gradient can outperform the neural tangent kernel regimes. Okay. So here, this is the spectral distribution of the random initialization of the weight matrix W. So this is the spectral distributions. So yeah, it's easy to derive this spectral distribution by like a Marchenko pass-through law. Okay, and by doing it in one-step gradient descent, then this spectrum is updated. Okay, so like a W0 is updated to W1, then this spectral distribution should be changed. So actually, if you do a large step one-step gradient descent, so there appears a spike here. So there appears a very large unspectral, so large eigenvalues. This corresponds to the feature direction. Okay. Now, so we assume that the target function is a single index model, whose direction is beta star. Then by performing it with a large step one gradient descent, we can find this direction beta star. So then this spectrum, so here, this spike corresponds to these directions. So the So eigenvector corresponding to this spectrum is beta star. Okay, so if the step size is very small, so maybe this there doesn't appear a spike. This point will be included in the bulk of the bulk of the spectrum. So then yeah, we cannot distinguish the signal and the noise. But by using the large step size, we can find the directions. Then by these mechanisms, so we can show that the large step, one step gradient, then we obtain a better performance than the neural tangent kernel regimes like this. Okay, so this is almost a minimax optimal rate for the single index model. Okay, so yeah, of course, in that situation, so we could do a kind of analysis by one step gradient descent. But for more general settings, we need more theories. Like if we don't assume the single index model as a target functions, then the optimization becomes much more difficult. So actually, the optimization on the mean field regime is highly non-convex. So we should overcome the non-convexities. That is a challenging problem. So our group, so actually, so ATSI initiated the mean field range band dynamics. So the mean field range band dynamics can analyze that kind of situations. Okay, in this AI stats papers, we have shown the linear convergence of the mean field range bands. Following this paper, we have published the main papers like this. So simultaneously, we have also analyzed some statistical properties of the neural network trained by mean field range band or other range band dynamics. Then we have shown that neural network can be better than the kernel method in these papers. Okay. And moreover, recently we got nice result on a propagation chaos. Some details will be presented by ATSI, but here I will give just overview. In the mean field range band, what we solve is to minimize these objective functions. Okay? So f is a convex function defined on a probability measure space, and we add some entropy. So then we want to minimize these objective functions. So because of this entropy term, so then objective becomes strictly convex. Yeah. So yeah, what do we want to minimize these objective functions? So why this is important? So this is related to the optimization of a mean field neural network. So as I said, a mean field neural network is given by like this. So if you take the width m to infinity, then this finite sum will converge to this integral form, where mu is a distribution of the parameters. So in other words, so we lift up the problem from the parameter to the distribution of the parameters. Okay. So if you look at the parameter itself, this is a very non-linear problem. But by taking m to infinity, so we obtain a kind of a linear model in infinite dimensional space. I mean, so this is a linear with respect to the distribution of the mu. So then we obtain an infinite dimensional linear model. So if the loss function Li is convex, so then the objective function is convex with respect to the distribution mu. So yeah, you can see that this problem is reduced to this problem. Yeah, okay. So then how to solve this problem? Then there appears a mean field range bounds, which is given by like this. Okay, so if you neglect this Brownian motion term, so if you look at this drift term, this is just like a Wasserstein gradient flow to minimize f. Okay, so this is just a Wasserstein gradient, and this is just a Wasserstein gradient flow to minimize f. But because this is there is an entropy term, so we have a Brownian motion term. So this is very important. The Brownian motion term is very important in our analysis. Okay, and you see that this Wasserstein gradient is depending on the distribution mu t. So mu t is a distribution by xt. So this is our distribution dependent SDE. Okay. So actually, so if you write down the Fokker-Planck equation of the distribution mu t, then it becomes like this. This is exactly the same as the Wasserstein gradient flow to minimize the objective L. So this is the Wasserstein gradient flow to minimize L. Yeah. So then it is expected that if the objective is convex, maybe the solution mu t will converge to the global optimal solutions. Yeah, so actually we can show that. And also we can show not only the convergence to the global optimal solution, but also the ratable convergence. To show the ratable convergence, so in our paper, we have developed like an entropy sandwich. So actually ATSI embedded this entropy sandwich. And so that mu star will be the argmin of the mu, the objective functions. Then the difference of the objective function is the same as the KL divergence between mu and mu star. So this is not so difficult. So this is the almost a trivial point. The non-trivial part is the right-hand side. So this objective can be bounded by the KL between mu and P mu. So the P mu is the proximal Gibbs measure, which is defined by like this. So the proximal Gibbs measure is the minimizer of the linearized objective. Okay, we linearize the objective f by taking its derivative. Then we have a kind of lower bound of the objective. So because the function f is convex, so yeah, this is the lower bound of the objective f. So P mu is the minimizer of the lower bound of the objective. So then KL between mu and P mu is larger than the KL between mu and mu star. Yeah. So this is an entropy sandwich. So now we assume that the P mu, the proximal Gibbs measure, satisfy the log Sobolev inequality. And through the very simple calculations, we can show the exponential convergence of the objective. So yeah, the mu t will converge to the global optimal solution in exponential order under the log Sobolev inequality condition. Yeah, and moreover, we have obtained a kind of a propagation chaos result. So here m is the number of particles. So okay, so we assume a distribution mu t by m particles. So this means that instead of infinite width neural network, we consider m width m for finite width neural network. Then we also have a convergence. But so here is an additional term which corresponds to the particular approximation errors. We can show that this particular approximation error is uniform over time. So it is basically 1 over n. Okay. So the more details will be presented by Atsushi. Okay. So the analysis of the mean field arrangement can be applied to very general situations. But if we consider more like a structured situations, I mean, if you assume some like a very specific structure on the target functions, we can obtain a much more like a detailed and refined analysis of the convergence or the gradient descent method. Okay, now we again go back to the Gaussian single index model like this. Okay, target function f star is the single index model like this. So if you know that the parameter theta, so the direction theta, then the problem is reduced to just a one-dimensional problem. So yeah, this single index model is a good benchmark to see the effectiveness of feature learnings. Okay. Well, so now we assume that sigma star admits Hermite polynomial expansions. Then the maximum degree of a Hermite polynomial is denoted by P, and the smallest degree is denoted by K, which is known as the information exponent. Okay. So for this problem, if you use the kernel method, the sample complexity is lower bounded by d to the p. So this is the lower bound of the sample complexity. But if you don't consider anything on the computation complexity, the sample complexity for the neural network is given by order d. So actually, by using like a mean field arrangements, you get this sample complexity. So we can show that. But however, in general, so maybe the computational complexity would be like exponential to d to get this sample complexity. So what I'm saying is that maybe there is like a trade-off between statistical complexity and computational complexity. To obtain the better sample complexity, maybe we need to pay more computational complexity. So our question is this true or not? So yeah. So actually, in this situation, for the single index models, we can obtain a much better computational complexity to obtain this sample complexity. Yeah. Okay, so I want to explain that. Yeah. So remember that information exponent is defined by the minimum order of Hermite polynomial expansion of the link function. Okay. So sigma star is expanded like this. The minimum order is denoted by k, which is the information exponent. Okay. So for these situations, okay, the lower bound of the computational complexity and the sample complexity is given by like this. Okay, to characterize this lower bound, we defined some queries. Okay, one is the correlation statistical query. Another one is the statistical query. Okay, the correlation statistical query is defined by like this. So it is an expectation of expectation of phi x and y. So this is like correlation between y and some function phi x. So phi can be chosen anyway. So we choose some function phi, and then we calculate the correlation between phi x and y. Suppose that if the algorithm can get estimated with this query, so then we say did that algorithm can obtain can ask the correlation statistical query. But so in practice, we cannot compute these expectations. So we need to estimate this from the finite data point. Maybe we have an error tau, which is like a 1 over squared n. Okay, so we estimated this correlation by n data points. Maybe we have a 1 over squared of n errors like this. The statistical query is a much stronger query, so which is given by the expectation of any function phi of xy. So phi should be bounded by like a 1 or something like this. Okay. So then suppose that the algorithm can get a CSQ, and so as long as that algorithm can is a polynomial order requires only polynomial order computation, then the sample complexity n should be low bounded by d to the k over 2. Okay, so maybe if you pay the exponential order computation with respect to the dimension d, maybe this lower bound could be much smaller. But as long as your algorithm is polynomial order with respect to the dimension d, then you should pay the sample complexity like this. So n should be low bounded by d to the k over 2. So if the algorithm can only get a CSQ, okay. But for the SQs, for SQ framework, this lower bound can be much smaller, like d. Okay. And so here, so why I'm talking about the CSQ? So that is because the stochastic gradient descent is included in the CSQ. Okay. So now we are minimizing the squared loss, and now we take the gradient over the expected squared loss. We can see that here is the statistical query. So the other part is independent of the target function y. So yeah, we are only interested in it here. So this is a correlation statistical query. So then by using the result in the previous slide, so by using this result, so if you use the SGD to optimize a neural network, maybe you are suffering from this lower bound. So you should pay d to the k over 2 to get good estimation errors. Okay, so actually the so-called smooth SGD can achieve this lower bound, but we cannot go beyond this lower bound. So as long as you are using the vanilla SGD. But however, so we can show that if you use so-called batch reuse technique, so you modify SGD a little bit, so then you can go beyond the CSQ framework. Then you get almost order D sample complexity. Okay, so what is the batch reuse? The usual SGDs, you get a data point, one data point, and then update the parameters, and then you throw out the data point, and then you observe a new data point, and then update. So you use the fresh data only once. So that's a usual SGD. So that is included in the statistical CSQ framework. But you use the same data 2 times. Right? You observe the one data point, and then you update the parameter by gradient descent by 2 steps by using the same data point. Then so you can easily check that it's not included in the CSQ. So then you can go out of the CSQ. Actually, you can get like a order D, so up to polylog D and orders. Okay, so this is a near information theoretic lower bound. Well, so for this batch reuse and online SGD settings, the sample complexity is almost the same as the computation complexity because the number of iterations is almost the same as the number of data points you observed. So yeah, so you can see that by using the feature learnings, you can obtain a smaller complexity for both statistical and computational complexities. Okay, so we have applied a similar argument to the in-context learnings. And I skipped the details. So what we have obtained is that the transformer with nonlinear attentions like a softmax attention can do a feature line in the test time. In the test time, okay, so we present some instruction in the prompt. Then even though the transformer do not update their parameters, they can do a kind of a feature learning in a test time. Then we obtain almost information theoretic law in the test time. So yeah, but I skip the details here. And also we have developed a new alignment method for LLM and diffusion model. But for the interest of time, I skip this. Okay, so then finally, this is the last topic I want to present. Yeah, finally, I want to talk something on the Monte Carlo search. So this is about the test time scaling. Yeah, this is the recent result in the ICML 2025. This is a joint work with Juno Kim, who was the master student in my group, and Denny Wu and Jason Lee. Yeah. Okay. So test time scaling is very important nowadays. So actually, like a deep seek and like a deep thought. So in many foundation models, and recently they are focusing on the test time computations. So that means that if you spend more computation in the test times, you can solve the very difficult reasoning tasks. Okay? So this is called the test time scaling. Okay? So actually there is a cap, but if you spend, so there is like a monotonically increasing the trend. So by spending more computations, then the accuracy is going up at some point. Okay. So then we want to give some theories on this phenomena. Okay. For that purpose, we consider very simple situations where the reasoning task is modeled by Markov chains. Okay. So maybe this is a question, then the answer is X out. So we start from X in, then we want to traverse the logical steps, then we want to reach the final answer X out. Okay. So that the one step of Markov process, Markov chain is one logical step. So yeah, so each node is just one logical state. And moreover, we assume that this Markov chain has a cluster structures. So each cluster has m nodes, okay? And so we assume that it's easy to move inside these clusters, okay? But however, going between this the cluster is difficult. Okay, so this inside the cluster, so this is an easy logical task. It steps. Maybe so there are a lot of equivalent statements, so then it's easy to go to the such equivalent formulations. Yeah, so just moving around in the cluster is very easy. But so there is some non-trivial logical steps. So to go across this non-trivial logical step is difficult. So we assume that the probability of the Markov chain to go through this edge could be very small. Okay, so here is more about detailed the figures. Okay, so suppose that so each cluster has m states, and the probability. So the transition probability inside the cluster is given by 1 over m. So this is our assumptions. And then the transition probability between the cluster is denoted by epsilon. We assume epsilon is much smaller than 1 over m. So this is a non-trivial step. It's very hard to find this path. Okay, so because the probability to go through this edge is like epsilon, which is much smaller than 1 over m. So it's very hard to find this edge. Okay, so and this is the Markov chain behind the data. So first, so our model must estimate this Markov chain from data. So during the pre-trainings, so we see a lot of logical transitions. Then we need to estimate this Markov chain from data. So then the first question is, can we estimate this Markov chain from data? Okay. So actually, so it's very easy. So we can estimate this Markov chain by using Granny descent. So okay, so now the model is very simple model. So we consider just softmax models. So this is basically logistic regression. So here X is one hot vector. So one hot vector of logic state. Okay, so we consider this softmax models. Then so we minimize the likelihood. We minimize the negative likelihood functions. So by using the Granny descent, just it will converge to the global optimal solutions in a polynomial order time. Yeah, then we can identify this Markov chains. So after you identify this Markov chains, then so the next question is so how long time so you should pay to reach the X out from X in. So you start from X in and you want to go to X out by running this Markov chain. So how long time? So how long is the hitting time starting from X in to X out? So the expected hitting time is given by like Km over epsilon. Okay, Km over epsilon. So the intuition behind it is that behind this is that to get out of one cluster, you should pay like M over epsilon times. So by after the M over epsilon times, you can get out of one cluster. You can transit to the another clusters. So then, so I should say that the capital K is the number of clusters. Number of clusters is denoted by K. So there are K clusters. To go to one cluster to another clusters, you should hop K clusters. So then you should pay the K times M over epsilon time. Okay. So then what I want to say here is that if epsilon, the non-trivial hop of the logical step is very small, this probability epsilon is very small, so then this hitting time could be very large. So in other words, it is very difficult to reach the final state X out. So we want to increase this probability epsilon. So then it becomes much easier to go to transit this between cluster edges. So by doing so, we do a search algorithm. Okay. So this is a kind of a Monte Carlo tree search. So in a post trainings, we do tree search, and then we find such a sparse edge. Then we increase the probability of this transition, probability of transition on the sparse edge. So the algorithm is written by like this. Okay, so this is a little bit very small. Okay, okay. So the idea is very easy. So here T0. So suppose that there is a time T0. So T0 is appropriately chosen. Okay, so if the time T. So we run the Markov chains. And so if the time T is smaller than T0, so this is yes, so this is appropriately chosen. So then you may visit all the points in the clusters. Okay, so maybe you can visit all points in the clusters. So if the time T is small, so then you are within the clusters. And so if by taking enough time, so maybe you visit all the states in the clusters. But so then so by doing so you can identify the cluster structures. But if the time T is sufficiently large, if the T is larger than some threshold T0, then you have already visited all nodes in the clusters. So after that, if you find a new nodes, so it must be outside of the clusters. So then, that means that you could find the sparse edge. So then you add this edge to the estimator of the sparse edge. So then you can obtain a kind of estimators of the sparse edges. Okay, so here's more details. Here's more intuitive figures. Okay, suppose that T0 is like m times log m squared. Then until time T0, you will be within these clusters. So you will never go out of these clusters. Okay? And also, so you will visit all the nodes inside of these clusters. Then after that time T0, if you if you find a new edge, if you find a new state, so then this new state must be outside of these clusters. So this edge must be the sparse edge. So we add this edge to our sparse edge estimators. So yeah, by running this algorithm many times, then you will find all sparse edges. Okay, so yeah, then in other words, you can identify exactly recover where was the sparse edges. Okay, so after that, after you identify the sparse edge, so we increase the transition probability of that sparse edge by using the PPO, like proximal policy optimization method, which is given by like this. The objective is given by like this. Here, so the A hat is advantage functions, like something like that. So if the x0 and x1 is the sparse edge, so which has been already estimated by the search algorithm, then so A hat is 1. If it's not a sparse edge, we set A hat to be 0. Okay, this is our advantage function. So then we maximize the expected advantage functions with some clip. So we put some clip so to prevent some divergence of these density ratios. Okay. So actually, this maximization problem can be done by just the gradient descent. So just by technicalities, we use a sign gradient descent. But anyway, by gradient descent, we maximize this objective functions. Then you can increase the probability to transit the sparse edge. So actually, so what we have shown is that the transition, the hitting time, the expected hitting time between X in and X out was given by the Km over epsilon. But by using this, after applying this PPO optimization, so PPO, then this is improved to the Km over epsilon max, where epsilon max is like 1 over m. So in other words, so we can increase the probability epsilon to almost 1 over m. So then the transition probability for the sparse edge and the transition probability inside the cluster are almost the same. So you can find the sparse edge more high probability. So then the test time computation could be much improved. Okay. So in other words, you can find a path from X in to X out more easily. Okay. So here's another difficulty. So if this is a possibility. So then, so here's the difficulty. So if you don't have the entire graph information, so you only have like a neighborhood information, then you cannot solve some logical problem in a polynomial order time with respect to the number of clusters. So this is given by like a SQ lower bound. Okay, so I want to finish my talk. Okay, this is summary. So we have considered many feature learning problems, and yeah, I hope that during this workshops we can discuss more. We can discuss more on the deep learning theories, and I hope it will connect to lead to some more better development of methodologies. But even though we cannot come up with some new methodologies, but maybe just developing a new learning theory is already very informative. So then I hope you will enjoy this workshop. So yeah, thank you very much.
Yeah, okay, yeah. Thanks, speaker, for great talk. So do you have any questions or comments from audience?
Just a very small questions about the CSQ analysis of the SGD. Do you consider only regression model, or is that also applicable to like classifications?
That's an interesting problem. Also, nice question. So if you change the loss, so not the squared loss, then the result is different. For example, you use like an exponential loss, so something like that. So then maybe the information exponent can be lowered. So you get a so-called generative exponent. So yeah, of course, we can consider like a classification, something like that. But for the classification, the problem is already different. So yes, so basically we are considering the regression problem. But yes, so like the input X is a Gaussian, then and also so there is like a CSQ or SQ queries. So if you use like an exponential loss function, so then maybe the SGD would be outside of the CSQ. Then you get a different result. Yeah.
Thank you. Since I'm curious about the generalization, so let me discuss later on.
Yeah.
Any other questions? Or maybe we can have one short question. Okay, so yeah, let me ask one short question.
No questions online?
Oh, okay, no questions from the Zoom?
No.
Okay. So yeah. So thanks, speaker, again.
Yeah, thank you very much.
I want to thank the organizers for putting together an amazing program and having me here today. And thanks everyone for coming to the talk. So today, I'll talk about learning neural networks in high dimensions. And this is joint work with Gerard Benarous, my student Murat, and my former student Denny, who is, I think, also in the audience, or maybe late, I don't know. In particular, I want to characterize the learning dynamics in quadratic neural networks, which I will define in detail, and when the neural network is trained by stochastic gradient descent. So I'll make different modeling assumptions, change the statistical model, and try to answer questions like why does scaling laws emerge when we are training neural networks, and how does different data structures affect the learning dynamics, and how does feature learning interact with the scaling laws. And this is also a work that is in the feature learning regime, just like Taiji mentioned in the previous talk. It's kind of trying to capture the power of neural networks. Okay, so let me start with scaling laws. So what scaling laws are, is these are actually methods that when you're under a compute budget, you want to tune some of the model parameters. For example, the number of parameters that is optimal given your compute budget. So we would see curves like the following here, where you have the population error on the y-axis, on the total amount of compute, and the x-axis, the log-log plot, and different curves correspond to different different neural networks with different width or the number of parameters. And what you're essentially trying to do is you're trying to find, given your compute, you're trying to find the neural network architecture that is optimal for you. And that would, in this case, if you think about it a bit, it's quite easy to see that the optimal one would be the one that becomes horizontal right at your compute budgets. So that would be the width that you would be choosing. So ultimately, these types of curves that you see that is kind of like a smoother type of curve, especially around the later areas, it arises because the loss depends on the number of iterations and the number of parameters according to the following equation. So this is basically like a power law decay in the number of iterations, that would be T. Another power law decay, that's like the width of the neural network, that would be capital N, and the minimum achievable error, that's L infinity. Now, C1 and C2 are called the scaling law exponents, and they depend on various things, and we're going to extract their dependence to the model later on. But ultimately, you want to actually get a sense of why these type of risk curves actually arise in practice. So there was also earlier work attempted to explain this phenomena and mainly considered linear regression setup. So it's actually that it's like a random features regression where you use a sketching matrix on the input and then do linear regression on top. And that's kind of the model that was used. In this model, you're not training the feature map. So that's basically, there's no feature learning in these type of models. So what we want to do is we want to understand this phenomena within the feature learning framework, or use a model that actually admits feature learning that can capture why neural networks actually work. And we also want to see how feature learning framework interacts with the scaling laws. Okay, so let me formalize the setting a bit. So we're going to consider a student-teacher setup. So this is a kind of like a machine learning theory terminology for model misspecification. Data is generated according to this model. So this is like standard supervised learning problem. Y is our response, or the label. Response is more accurate. And X is the input, which is d-dimensional, and F star is the unknown target function that we're trying to learn, and there is also some noise. And we assume that usually, in also many of the papers that I co-authored prior to this work, F star depends on the input only through one direction. Theta is an unknown, and we also have a nonlinearity on top sigma, but the target depends on the input only through one direction, theta, and that's actually quite a restrictive condition. Now, theta and sigma is going to be learned by a student network, and that would be like a student neural network. A student neural network does not have to look precisely like the teacher one that generates the data. So that's, we mostly focus on two-layer neural networks of the following form. So W here in this equation would be the first layer weights, and then you apply a nonlinearity phi on top, and then the second layer weights V. So how do we learn it? Let's say we are only learning the first layer weights, and you basically choose a loss function like squared error loss and do online SGD, online stochastic gradient descent on this first layer weights. So an example of this type of a model, so single index model, is, for example, phase retrieval, right? So in the phase retrieval problem, the nonlinearity is a quadratic. We subtract 1 here just so it has mean 0 under this input distribution assumption, which is Gaussian. But you're essentially trying to learn a quadratic teacher network with a quadratic student network. So that's the classical phase retrieval problem. I'll come back to this example later on because we are also going to stick to quadratics throughout this talk. But our understanding on learning single index models is actually we understand what's going on with their risk curve quite accurately, and they are characterized in Benarouz 2021 paper that introduced the information exponent. When you're running online SGD and squared error loss and learning these models, the risk curve that you will see looks like the step function. Basically, there's like a long search phase. It's like a plateau, and then a sharp descent phase, much shorter than the search phase, followed by it. So it's like this step function behavior arises. And for example, in gradient, if you're using gradient flow, you would have a search phase that's like roughly of log d time and descent phase roughly of O1 time. And if you're using SGD, because of the discretization error, you would multiply this. This would be d log d and this would be d. But it's just that the search phase is much longer than the descent phase, and we see this step function behavior. But this does not really match with what we see in practice. As I mentioned in the introduction page, is basically that we see these power law dependence, and power law is like a smooth curve rather than a step function. So what is going on here is that we actually made a data assumption like so that is too simplistic. So these type of data models, I mean, it's sort of interesting from a theoretical point of view, but when it comes to real data, they fall short. Yeah. So in this one, it's not. Okay. So actually, I have a plot. I have two plots next to each other. One of them is going to be log. The other one is just like plain. So, all right. So what essentially is happening is that this assumption falls short. So this theta is called index, and there is only one of them. So there's only one direction that the output depends on the input. So we want to actually come up with a model that captures at least some of the dependencies in the real data, and that would be through an additive model. So from single index to additive models are more kind of complex, and it can capture some of the more details in the real data. I'm not claiming that they can capture everything in real data. It's just that they will be able to capture the scaling law phenomenon that we observe. So for example, in an additive model, instead of a single index, just like this one here, we have multiple indices, theta j's, and that would be our many indices in the additive model. We stick to the same nonlinearity here. That's restrictive, but that will be fine for now. And we also have the mixing coefficients, lambda j's, is kind of like determining the contribution of each of these indices to the overall model. And because lambda j's are different, you can think of them as signal strength. Each of these theta j's will be learned at a different time. So you'll basically end up with a bunch of step functions just like so. So they have different plateau length because their signal strength is different. And ultimately, when you combine them, you'll get a cumulative loss that looks like a smooth power law decay. Okay. So this is kind of the rough picture that what we expect, and we're going to stick to this model. So let me give you the the model in a more detailed way. So we will choose a teacher model that generates the data. That's the unknown target function f star is a two-layer neural network. Theta J's there are many of them, and R also scales with dimension. It's d to the power beta, where beta is in between 0 and 1, so R is actually large. And theta J's are R many, and we have a quadratic dependence to the input and the inner product of the input and the theta J's, and the second layer weights are lambda J's here. And lambda J, the mixing coefficient, or the second layer weights, decay like a power law. And the power law decay is like J to the negative alpha, where alpha controls how fast the decay is. And so this alpha parameter will come up a lot, so it's good to keep that in mind. So it's kind of how fast the lambda J's are decaying to 0. Okay, so this is the model that we will consider. So this corresponds to choosing basically degree 2 polynomials, or in other words, just like Taiji introduced in his talk, information exponent equals to 2 case. So this work only considers information exponent 2, and for larger information exponents, Denny will actually talk about it in the afternoon session. But the behavior for the information exponent equals to 2 is very much different than a larger information exponent case. In particular, the dependence of these theta J's and the student width kind of decouples in the higher information exponent case, whereas in this work, quadratic case, they are kind of like the dynamics are coupled, so the analysis becomes somewhat more difficult, or at least it would be a different analysis, entirely different analysis. Okay. So for the student network to learn this kind of model, what I will consider is, again, a two-layer neural network. So I have this student model here where we subtract the norm square of the WJs just because we want to have a mean 0 network as well, just like the target function. So you notice that there is actually no second layer weights here, or second layer weights are kind of frozen to be 1. It's just that we only have the first layer WJs to be learned, and that's going to be an important point later on when we come up with the algorithm. I will focus initially on the light tail case when alpha is greater than equal to 1/2. This is sort of an easier case, but also like gives us a nicer and easier to interpret results. And I'll tell you what happens later on when alpha is actually less than 1/2. That would be the heavy-tailed case. Okay, so a few definitions before I show you some of the results. To measure the performance of the student neural network, we look at the expected squared error loss, and that's basically the population risk under the squared error loss. And we will initially consider a warm-up algorithm. So this algorithm is much easier to analyze and understand compared to a real algorithm, but it's going to give us a lot of the intuition what to expect, and also the results will be cleaner. And that would be the gradient flow on the population risk. So we have the first layer weights WTs, and we consider this algorithm. Note that this is a gradient flow, so it's not a real algorithm, so we cannot talk about the computational cost yet. But we will talk about SGD later on. And the gradient flow is initialized with Gaussians. This is standard initialization. It's also used in practice. And just to ease the notation a bit further, risk at time t will be called R of t. Okay, so I will have to introduce a notion that's called polar decomposition. So it's basically that at time t, your weights are WT, right? So this is the student neural network. And you would do polar decomposition and get the rotational component that is UT. So this is an orthonormal matrix. And if you're not familiar with the polar decomposition, just think of SVD is just that is like an orthonormal matrix that's like the basis for it's like a basis for the column space of WT. And that's actually what I'm going to rely on. And using this rotation component UT, I will define the alignment between the student weights and the jth index theta j. So the alignment between theta j and the weights at time t is going to be the Euclidean norm square of UT transpose theta j. So UT is orthonormal, and I forgot to mention that theta j's are also they're orthogonal to each other. So this, and they're unit norm, and these are this norm square is going to be a quantity that's in between 0 and 1. So 1 means that we have perfect alignment. 0 means that theta j is not in this column space, so we have no alignment whatsoever. So this is a quantity that's in between 0 and 1. We want this to be 1, basically, so that we can say that the index theta j is kind of like captured by the student network. Okay. So here is a warm-up result on the gradient flow. So we consider a student width that would be RS. So let me take you back here. The teacher network width is R, and the student network width is RS. So we will consider a neural network and a student neural network that's not doesn't have like a excessive width. And we will define this time scale parameter that is looking like this. So gradient flow will achieve the following guarantees. So first of all, we're going to look at the alignment. So the index j, meaning theta j, is going to be recovered at time t, scaled with the t effective, the time scale parameter, following this equation. So this is kind of the alignment is characterized in terms of time, alignment between the student network weights and the index j. And there is an error that goes to 0 with dimension. And using this, we can also characterize the risk curve at time t, again scaled with the time scale parameter t effective. That would, the risk curve would look like essentially this plus some error term that goes to 0 with dimension. So just like I kind of advertised this in the introduction, you notice that the risk actually has like the form that's like summation of step functions, right? So that's kind of where for each of the indices you get a step function, and their summation leads to a smoother thing. And that smoother thing, the smoother curve, would appear as you let dimension to infinity, and this is kind of the asymptotic result. The risk scaled with risk at time t scaled with log d is going to converge to maximum of these two terms. So now I'm going to make a few remarks. Just like looking at the alignment, we can see that the theta j is going to be learned at time t effective divided by lambda j. And this gives us a step function behavior. For example, task 1 corresponds to index 1, index 2, index 3. They will be learned at different time scales, and together their summation will give us a curve that looks like smoother and smoother as the time goes by. The scaling law behavior in practice, if you have read the applied papers, actually use summation of two terms, whereas I have a maximum between two terms. So that's that looks a bit different from the practice. But since I have this omega in front of this equation, it's basically that summation and the maximum are the same thing within this notation. So that kind of so in case there's a question about that, this is the reason. So maximum and summation there would be equivalent up to a constant because of this omega. And we would see this basically as T was then the time scale and RS was the student width. So if one of them characterizes the optimization time, the other one is the number of parameters in the model Mahdi.
Or so I'm just like wondering if n goes to infinity first, then d is going to infinity, or
Yeah. So this is exactly. Yeah.
I see. Got it.
Population gradient flow. This is and then I have like some error term that's here, and then I let d to infinity, and this is what I recover. And this log t here is just like just the scaling that comes from this t effective. You're right. And yeah.
I also have a quick question. So actually, when we consider the square to the iteration function, as you mentioned, it's also from a phase retrieval, also belongs to this regime, right?
Mm-hmm.
So if we use AMP to do this procedure, so I'm wondering, so how does the curve will behave?
I don't
It's
know of
also,
an AMP analysis where the teacher network has like R indices.
Okay.
I know the one that's like just a single index, like it's just a phase retrieval, right?
Yes. If we consider,
I don't know if there was any later paper that looks at excessive
I
bits.
see. Okay.
This was like a different framework, but I should. But we're gonna stick to SGD, so it's not AMP work. Yeah.
Okay.
Okay, so this is kind of promising in the sense that we can get the scaling law behavior in the gradient flow. But as I said, this is not a real algorithm. This is like you're running gradient flow on the population risk, like infinite data, a continuous time process. So there's a lot of assumptions going on there. So for the real one, we have to modify the algorithm that we use in practice a bit. I will stick to online SGD, but on the Stiefel manifold. That is basically, and then also relying on two steps. And I'll explain why I need two steps, but let me actually go through the algorithm. First, the algorithm is online SGD. You, at each iteration, you would take a gradient step, and then you would project your W back to being orthonormal. So this is, you can think of this, if W was like a vector, this step is just like this, just like a normalizing W to be on to stay on the manifold. So this is the first step. On the first layer actually is just online Stiefel SGD. But since we kept W orthonormal throughout this process, there is no way that this type of algorithm can learn lambda j's, the second layer weights of the teacher neural network. And for that, we actually need to scale and rotate the W's in the first layer weights of the student neural network. And that would be the second step of the algorithm. And for this, just for technical reasons, we need to do this on a new batch of data. So we do this with T iterations. This is online SGD, so you use T data samples here. And then we would do this in a batch form on over N sub FT many data samples. And these are kind of independent and fresh. So this second step is called the fine tuning, and it's just based on this equation here. Again, just kind of training the second layer after training the first layer. So it's more accurate to think of it that way. But for all kind of interesting, like sample complexity purposes and the results that I'll mention, this is like the number of samples that you use here is going to be negligible compared to the first step. So this is actually like this step that relies on N samples is going to be much more kind of sample efficient in terms of sample complexity. So sample complexity will be determined by the first step. Again, a few things here that pretty much everything will look the same, except that now, instead of the time scale, I have the iteration count here. So T determines the iteration. And R of t is, again, this is measured as iteration. If you want to kind of convert it to time, you would multiply with the step size. And alignment between Wt at iteration count t with theta j. And this is the minimum achievable risk, where I'm assuming that the student width is much smaller, or at least smaller than the teacher width. So when R opt is the minimum achievable risk, so the result looks like as follows for the online SGD. For the same time scale parameter that is given here, and we choose a step size that's O order 1 over D, and the number of samples you use in the second step looks like this. You see that it's like logarithmic in dimension, and RS is O order 1. So it's much smaller. Then we get the runtime and the runtime complexity of the SGD as follows. So this is basically saying that if I run SGD O order D iterations, I would achieve a risk that is very close to the optimal risk, optimal achievable risk. And since this is an online algorithm, this also is the sample complexity that's going to also dominate the second one. So this is the overall sample complexity D. This result directly follows from the risk curves that the results that very much look like the ones that I showed you for the gradient flow. The alignment is given by this expression, where previously I had the time scale here. Now I have the step size times the number of iterations. This looks slightly different. It's just that I wanted to make it more clear, but it's also exactly the same as the gradient flow case. Again, the time is just replaced with the number of iterations times eta. So you see that you have the minimum achievable risk and summation of bunch of step functions. And as you take the limit, you would get the following scaling law behavior. Again, it's the maximum of two things, but the maximum and the summation are the same. So you would get a scaling law as dimension goes to infinity. So now I will show you a plot that's like a regular plot and a log-log plot and how it looks like. So on the x-axis, we have the number of iterations here. Y-axis is the limit trajectory. So the dashed lines here they correspond to this risk. And the solid curves correspond to the limiting behavior here. So you see that you would see the step function behavior, but as you take more and more iterations, and they would become like smoother and smoother. And the log-log curve, you would get the standard scaling law thing, but you also need to change the x-axis to compute and so on. But yeah, so this is kind of, maybe as a final remark, if you look at this, all the step functions would become 0 as you let t to infinity. So this summation would become 0, and you would achieve our optimal, the minimum achievable risk. And the sample complexity that I advertised here actually is a direct result just by analyzing this. You don't have to choose t equals infinity. You would have to choose t equals O order d because of the step size dependence, and this term would become 0, and that's where the sample complexity comes from. Okay, so I'll briefly talk about the heavy-tailed case. And the heavy-tailed case when alpha is less than 1/2 is a bit more difficult because your lambdas are not square summable. So that makes the problem infinite dimensional. There are a few things that will be different, and I color-coded them with blue. And so, for example, previously I needed O order 1 student width. Now I need actually a width that's like scaling with the teacher width, R. Student width divided by the teacher width converges to a constant. This constant phi determines your model's capacity. If phi is less than 1, you have less capacity, so you won't be able to learn. And if phi is greater than 1, you have more, like student network can learn the model. Step size changes a bit. and the sample complexity, which I'll talk about it a bit in the next slide, that also changes a bit. But ultimately, the risk curve looks like the maximum of two things now. The second one here is it depends on the model capacity. You see that if phi is greater than 1, the second term becomes 0. That's when you can achieve 0 risk. If phi is less than 1, meaning student network does not have enough capacity, then this term actually cannot be 0, so you cannot achieve 0 risk. Okay, so the first term, as you take more and more iterations, you would achieve, like the first term goes to 0 actually. Okay, so the behavior looks like this. When alpha is 0, you have the isotropic case. It's basically that you have all these step functions, but they go to 0 at the exact same time, so you would have like a sharp decrease like so. It's not like smooth, but as you increase alpha, the time that each of the indices are learned actually now becomes different, so you would get a smoother and smoother curve, as you see in these figures. Okay, so maybe a final remark on the sample complexity, because I wanted to kind of say like what happened in the feature learning regime, right? So the feature learning actually helps in the sample complexity. So that's where actually it matters the most. For example, if you did not have feature learning to learn this degree 2 polynomial, you would use like these square samples. In this case, for example, in the light-tailed case, the sample complexity becomes O4 D, whereas in the heavy-tailed case, the sample complexity becomes D times R to the 1 plus alpha. Now, the light-tailed case, when alpha is greater than 1/2, this is information theoretically optimal sample complexity up to log factors. When alpha is 0, again, that's optimal to learn a R-dimensional like rank R subspace. However, when alpha is in between 0 and 1/2, our sample complexity that looks like D to the R, D times R to the 1 plus alpha actually is suboptimal. So there is this extra factor of alpha that we kind of couldn't get rid of. It's kind of a artifact of the proof that is required to control the error bounds in the discretization error. Yeah, so this could be improved. Okay, I'll don't have much time left, so I'll briefly talk about the proof and give you an idea how things work. So just a reminder, we have the teacher network and the student network, and let's start with the gradient flow. We are considering the gradient flow here at first, and under the squared error loss, expected squared error loss. And the alignment is this quantity where we rely on the polar decomposition like this. So a few things that matter to us, and it's going to be more clear after Denny's talk in the afternoon. The inner products between theta j and wi actually are not decoupled in this analysis, which is not the case when you consider higher order information exponent. Now, also the dynamics are kind of the number of summary statistics that we need to keep track of is actually is infinity. And there's also different challenges in the discrete time that I'll go over. But ultimately, what matters to us is that, for example, just by looking at this summary statistic, like the alignment, most of the statistics that matter to us, the alignment, the risk, and all that stuff, can be tracked just by considering gram matrices. And one of the gram matrices that you can do, for example, that alignment can be seen as the diagonal entries of this gram matrix. Here, theta is the teacher directions, and UT is the polar component of the polar decomposition at student width at time t. So if we can actually keep track of these gram matrices, then we are actually good, and we can extract these statistics that we care about, That's basically one observation. The second one is that this particular gram matrix, because we stick to the quadratic case, is going to be evolving according to this matrix Riccati ODE. So the matrix Riccati ODE is given by this expression, and this somehow was previously used in the analysis of neural networks, but since we need to extract the scaling law, we need a precise analysis, and that requires a tighter control. And for that, we use a property that wasn't used before, and that's the monotonicity of the matrix Riccati ODE. So this monotonicity is like not the first kind of monotonicity that comes to mind. That would be the monotonicity that I'm talking about is as follows. If you initialize this ODE with two different matrices that has the following matrix order, one is kind of an upper bound to the other in terms of the matrix order, then this relationship between the trajectories actually is preserved at time t. And a figure that kind of demonstrates that is looking like this. This is kind of the level sets. The initialization is here, and initialization with a larger matrix is here in the dashed line. The solid one is the smaller matrix. As you evolve it with time, you see that dashed curve always stays inside the solid curve, kind of demonstrating this behavior. And ultimately, what you do is basically you upper and lower bound this gram matrix with something diagonal, at least the portion that matters to us. And that kind of makes the analysis decoupled so that we find an upper and lower bound and show that they match so that we get actually the precise risk curve and the scaling law. So that's kind of the proof for the population gradient flow. Very briefly, out of time, but the discretization is like, we're trying to kind of mimic the same and show that online SGD actually is close to the gradient flow. And the continuous time, this is the Riccati ODE that we have to kind of show closeness. And the online SGD corresponds to a update rule that is given like this equation. However, this equation turns out to be not monotonic in the sense that I showed in the previous slide. So for the step size that we consider. So we find another update rule that is monotonic in the sense of the previous slide and show that the Euler scheme that corresponds to the SGD is close to this monotonic update rule. And basically, the rest of the analysis kind of is similar. Okay, so with that, I will conclude. So this is basically a scaling law for the quadratic neural networks, and both in population gradient flow and the online SGD in the feature learning regime. The feature learning part matters because we gained quite a lot in the sample complexity. And that also like helped us reconcile some of the properties that we see in learning single index models to, and also what we see the risk curves in the practice. So a few feature directions is basically, this was just plain SGD. The effect of like any algorithm modification is quite interesting here, like how does the scaling law exponents depend on the momentum or the adaptive schemes and so on. Another thing is that when the data is more structured, like input is maybe not Gaussian, but has more information about the target through some covariance structure, how does that enter the scaling law exponents? That's another interesting question. And also, most of the existing literature is on regression so far. And what happens in the classification setting is also not clear, which I find quite interesting. And with that, I will conclude, and thank you so much.
Yeah, thanks, speaker, for great talk. So any questions or comments?
So there is something that I kind of am confused about. So this essentially, it does become like a low-rank reconstruction problem because the planted model, so I'm kind of surprised the condition number of the teacher doesn't show up anywhere, or somehow it's implicitly showing up, like especially in sample complexity, I would expect the condition number, meaning the ratios of the lambdas to show up somewhere, right?
Right, so it's a finite dimensional problem when alpha is, for example, alpha is greater than 0.5, right? So you don't have to learn all the indices to achieve minimum risk.
I see.
So that's like one way to see that is just like you have to, like you can truncate it at some level and you don't have to worry about the rest of the stuff. But in the prior analysis, I think there are analyses that the condition number is kind of like exponential and not nice, so it doesn't show up in this case.
Thank you.
So any other questions?
Thank you very much for a great talk. So if you remove the Stifel manifold conditions, so then maybe the analysis becomes very, very different. And is it difficult or not?
That's what we initially attempted. The error terms that you need to control in the SGD update becomes a bit nasty. So it's just for a technical reason that we kind of had to resort to the Stifel manifold. But I think, yeah, I am optimistic, but we attempted and couldn't do it. Let's put it this way.
Okay, thank you.
Any other questions? So questions from the, okay. So yeah, I have a quick question. So now you focused on the quadratic neural networks. So is it possible to extend to more generic activation function? So in other words, so how crucial is the choice of the quadratic activation?
Yeah, I think that question will be partially answered in Denny's talk in the afternoon session. So he's going to talk about like higher order information exponents. But this is sort of like the edge case that the analysis that is done in the higher order for the higher order information exponent does not apply to this case. So it's because of like the dynamics decouple and not decouple. That's kind of what matters. Our analysis is very specialized for the quadratic case. Mm-hmm. So this wouldn't apply to that, and their analysis wouldn't apply to this case.
No, okay, yeah, thank you. So now, any comments? Okay, so if not, so then, yeah, let's thank the speaker again.
Okay, thank you very much for introduction. So welcome back. I'm Sho Sonoda. I'm one of the organizers here, so thank you for attending. And I'm a senior research scientist at RIKEN. And today's title is Deep Rigid Transform. So let's start. So because this is a wrap-up workshop, I here prepared an overview of my research works. And I spent 7 years in RIKEN, and in my understanding, the team mission is to understand and improve the machine learning process. And in addition, I have a long-term personal goals. This is to develop information geometry for deep learning or AI. But it's a lifelong work, so yeah. And in 7 years, I did both theory and applications of machine learning. And today's topic is mainly about the rigid transform. So, but let me introduce briefly. So in addition to rigid transform, I have 3 preprints this year. In addition, I have 1 publication this year. So I don't explain this, but I also have some research topic in the geometric group theory for generalization analysis, or work using a quasi Monte Carlo for algorithm proposal. And recently, I also started working on the AI for math. This is an application of LLM, and we let LLM to generate the conjectures, mathematical conjectures in a formal language and let the LLM to prove them in Lin4 manner. In addition, I also did a collaboration with a quantum information guy and proposed some quantum machine learning algorithm with a theoretical guarantee. Okay, so let's start talk about the Ridgelet transform. So what is a typical solution obtained by deep learning? This is a big question I'm working for many, many years. And as you know, this is an illustration of a deep neural network. And we don't know how the parameters are assigned after the learning process of deep learning because the learning process is automated and it is conducted in a high-dimensional space. But as a mathematical object, we want to know how the functions are divided into layers, or maybe we want to characterize when deep learning is better than a shallow network. So that's the motivation of this study. And but of course, there's fundamental technical difficulties. I mean, let's say that modern mathematics lack techniques to deal with deep neural network, such as a very simple deep neural network, such as depth 3 network. It has more than 2 activation functions. Still, this form is super difficult to analyze for modern math. In addition, analysis of softmax is difficult too, and LLM is more difficult. So in a theoretical study, we usually assume that the layer number is just 1, or the layer number is infinity. This means the neural ODE, or sometimes consider random weights, or sometimes consider linear activation, or sometimes consider local linear approximation. But if you are an end user, maybe you want to know how to assign those A1, A2, A3, right? So that's a major motivation of this study. Fine. So in order to tackle the rigid analysis of a deep neural network parameter, I formalize the problem as a learning equation. Learning equation is a stronger form of a learning problem. Learning problem is just the loss minimization. But this formulation is an exact equality. So given a data generating function f or on data domain x to r, and given an arbitrary architecture of a deep neural network with parameter gamma, we find the parameter gamma of DNN satisfying DNN of gamma equal f. And if you are lucky, you can find the inverse transformation for this learning equation. And if we can luckily find the inverse transformation, I call it the Ridgelet transform. I call the solution operator to this equation the Ridgelet transform. So the Ridgelet transform satisfies if we substitute the Ridgelet transform of function f to the place of a parameter gamma, it reproduces the original function f. Okay. And classically, it is known, the classic Ridgelet transform is known for depth 2 fully connected neural network on Euclidean space. So in the first half, I will explain this classical Ridgelet transform. And then recently, we developed a Ridgelet transform for depth n generalized neural network on arbitrary G space X. So in the second half, I will explain the generalized version. Okay. Oh, by the way, you can stop anytime you want. And you can ask any question. So in order to introduce the Ridgelet transform, I first introduced the integral representation of a neural network. the upper panel corresponds to the ordinary depth 2 fully connected network. And here AI and BI and CI are parameters. And we can regard this sigma AI x minus BI as a basis function. So for single hidden layer neural network, we can regard this as a linear combination of units, basis functions. But in fact, the analysis of neural network is already difficult even for this single hidden layer network because those parameter AI and BI are inside a nonlinear function. So if we change the parameter AI, we cannot predict how the function itself will be changed because of the nonlinearity. So the bottom panel corresponds to the infinite width or integral representation neural network. This is a mathematical trick to linearize the parameter of neural network. The definition is given here. This is a linear combination of all possible hidden units sigma A x minus b with the weight function gamma. And here I assume gamma to be a signed function, not always positive. So because all the possible A and B are already presented, we don't need to choose which AI and BI to use. Instead, by weighting on them, by using weighting function gamma, we can choose which AI and BI to use indirectly via weighting on them. And the nice thing is that we have now a linearized version of neural network because if we twice this weight function gamma, then the function itself will be twice. And if we add two weight functions like gamma 1 plus gamma 2, then the function itself will be added like s gamma 1 plus s gamma 2. So then we have a linearized neural network without any approximation. Without means that if we choose gamma to be a linear combination of point masses, we can exactly reproduce a finite width neural network. So in this sense, this integral representation includes the finite width network. Okay, that mechanism of integral representation. So, and for this integral representation neural network, the inverse transform is known. This is correct, the Ridgelet transform. The upper panel is the definition of Ridgelet transform, and the second panel corresponds to the theorem stating that it is an inverse transform. So the definition of Ridgelet transform is given by functional inner product of a function fx and the feature map rho a dot x minus b. Here, rho can be different from activation function sigma. And fx is a function to be approximated by neural network. So it essentially measures the similarity between function fx and feature map rho a dot x minus b. And the theorem is that assume that activation function is a temporal distribution. Temporal distribution includes a ReLU or hyperbolic tangent or Gaussian or derivative of Gaussian. Almost all possible activation function is included in this class. So this is a very wide class of activation functions. On the other hand, assume that rho is a Schwartz test function. This is also called the rapidly decreasing function, and typically a Gaussian or a derivative of Gaussian. So the rho is very smooth. On the other hand, the sigma can be less smooth. And also assume that f is an arbitrary square integrable function on Rm. Then if we substitute the Ridgelet transform of f with respect to rho to the place of unknown weighting function gamma of a continuous neural network, it reproduces the original function fx up to the constant sigma and rho. And here sigma and rho is given by this expression, but it is essentially the bilinear form of activation function sigma and its dual rho, dual activation function rho. So as long as sigma and rho are not orthogonal, then you can normalize this term to 1. Then this equality is exactly equal to fx. And this formula has two meanings. The first meaning is that because this S of blah blah is a formulation of a continuous neural network, so we can, and the choice of f is an arbitrary scale integral function, so we can understand this formula as a universality of a continuous neural network. The second meaning is about the roles of a Ridgelet and the S transform is equivalent to the roles of a Fourier and the inverse Fourier transform. Maybe many of you are familiar with Fourier transform and its inverse. If we substitute the Fourier transform of f to the place of unknown frequency function of in an inverse Fourier transform, then it reproduces the original function f, right? So f of f z plays the same roles with Ridgelet transform. So Ridgelet transform encodes the function on Rm to the function on parameter domain. And Fourier transform encodes the function on Rm to the function on frequency domain. And the inverse Fourier transform decodes the information on frequency domain to the real domain, right? So continuous neural network operator decodes the function distribution of parameters to the real domain. Okay, they play the same roles. In terms of harmonic analysis, the Ridgelet and the Fourier transform is called analysis operator, and this S operator and F inverse is called the synthesis operator. Okay. So, and this is an example of a Ridgelet transform for the case of a one-dimension signal. So for the purpose of visualization, I prepare here a one-dimensional signal. Then the Ridgelet transformation result will be a two-dimension signal. And it typically has a positive and negative part. The red part corresponds to positively high intensity. A negative part corresponds to, blue part corresponds to negatively high intensity. So it's typically oscillating. And if you're familiar with wavelet transform, for one-dimension case, the Ridgelet transform is exactly equal to the wavelet transformation of signal. But if we consider more than two-dimension case, the Ridgelet transform is understood as a composition of a radon transform and a wavelet transform. So it has a very deep connection to the wavelet transform analysis. And if we use different types of rho, the encoding result looks slightly different. But as long as the sigma and rho are not orthogonal, then we can reproduce the original function f. Because if we let's see this reconstruction result, it has a trilinear form, right? It is linear in f and rho and sigma. So as long as this term is not zero, not degenerated to zero, then we can reproduce the original function f. But if sigma and rho are orthogonal, then the reconstruction result degenerates to zero function. Obviously, this pattern encodes the information of original function f, but the output is just degenerate to zero. So what we see here is the null space of a neural network. And Yes, the nice thing of a Ridgelet transform is that if the Ridgelet transform can explain the parameter distribution obtained by gradient descent. If we conduct a gradient descent with a finite width neural network and plot the distribution of parameters after the convergence, then you will obtain this kind of distributions. Here, the y-axis corresponds to A here, and the x-axis corresponds to B here, and the color corresponds to C. So this plot is more than 1,000 points or 1,000 parameters obtained from a finite width network. And obviously, it has a red part and blue part. And for example, those red points accumulate around the red areas in the Ridgelet transformation. And the blue points typically accumulate around the blue areas in the Ridgelet transformation pattern. And this is not a coincidence, but we can mathematically prove that the loss minimizer eventually converges to the Ridgelet spectrum. But in order to show this, we need to impose a regularization term. Otherwise, the solution, we have multiple solutions, but if you impose some regularization term, you can show the uniqueness of the convergence point. So what this means? This means that some people consider the parameter of neural network is somewhat a black box, but I don't think so, because this is just a transformation result of Ridgelet transform. So the understanding the neural network parameters is turned to understanding the Ridgelet transformation for the corresponding neural network. So that's an interesting point of this study. But Ridgelet transform is originally known only for depth to fully connected network. But of course, we now have a variety of different types of network architectures. So we want to find the Ridgelet transform for a variety of network. But there are no method before our study. It was originally found in 1990s, but they say they found it by inspiration. So in RICAN, we develop two threads of method. One is by using Fourier expression, and the other is by using group representation theory. And today's talk is, in the second half of today's talk, is this group representation theory version. The Fourier expression is also very strong because this method essentially turns the neural network into Fourier transformation, but it has a limitation. It is limited to only single hidden layer network because of the linearity of Fourier transformation. So it was major drawbacks of this method, but by using a group representation theory, you can find the Ridgelet transform for depth and case. Okay, so let's move to the second half. So the deep Ridgelet transform for joint equivariant machines. Okay, let's start from the motivation. Universal approximation theorems are central in deep learning study, but the proofs are given case-by-case manner. So we want to unify the universal approximation theorem for a variety of deep neural networks. That's the motivation. And to do this, we introduced the new concept, joint group equivariance of feature map. This is a new concept. I will explain later. Then the generalized version of a Ridgelet transform can unify the proof of universality. And the Ridgelet transform will provide a closed form parameter distribution, like a gamma equal R of F. And if we substitute this to almost an arbitrary deep neural network, it reproduces the original function f. And in the end, this formulation includes not only deep, fully connected network, but it also includes a deep group convolution network and also a new quadratic network that is not known to be universal. Okay, this is an overview of the study. And those are a list of key mathematical tools used in this study. So this topic is mainly based on the group representation theory, and I will use some concepts like irreducible representation of group G or Schur's lemma. This is a characterization of irreducibility of group representation. And I also introduced the joint group equivariant feature map, and finally derive the Ridgelet transform. Fine. So let's introduce the joint equivariance of feature map. This is an extension of a well-known group equivariant map. So let's start from the definition. Let G be a group, and X, Y, and Z be G sets. G sets means that the X, Y, and Z are sets, and they have a group action by G. So on each set, they have group actions. And I will use X as the input space, and Y to be output space, and Z to be a parameter space. And any feature map, phi, the feature map is a mapping from data and parameter to output. And we call a feature map is joint group equivariant if it satisfies this identity. This is if we act a group G on data and the parameters simultaneously, then the output of feature map will be acted by group G. Right. So in a classical setup of group equivariance, we do not act group G on parameters. The parameter is fixed. So if we rotate the input, then the output will rotate it. But in our setup, joint group equivariance setup, we also allow group G act on parameter. So, this joint G equivariance is a generalization, extension of a classical G equivariance. If we assume G dot Gz to be a trivial, I mean, the G dot Gz equal Gz, then it reproduces the classical group equivariance, right? So, and one motivation to consider this extension is a fully connected network. You know, the fully connected network is a typical example that is not group equivariance in a classical sense, but it is joint group equivariant. That's a major motivation to consider the joint group equivariance. And I will explain it later. So, and in addition, not only the feature map, we also consider the integration of feature maps. Oh, yeah?
I have a question on the example. Because the group action here is multiplication by scalars.
Not limited to scalars.
But you are using the fact that it's the ReLU, yeah? For the...
Sorry?
Does it need it to be the ReLU for this equivariance
It does
property?
not need to be ReLU.
Okay.
This sigma can be hyperbolic tangent or almost all nonlinear activation function.
Okay.
Yes, and not only the feature map, we also consider the integration of feature maps in order to linearize the parameter again. So to do this, we also, in addition, assume the G to be a locally compact group. This assumption is a sufficient condition for the group G to have an invariant measure. So, and assume that the X and the parameter space Z are G spaces with the invariant measures dx and dz. And in order to consider integration, we assume that the output space is a Hilbert space with a G action. And assume that the phi is a joint equivalent map. Then for any parameter distribution gamma, define the joint equivalent machine, M of gamma with respect to phi as an integration of a phi with respect to parameter z with the weighting function gamma z. So this is a linear combination of feature map from x to y with parameter z. Okay. Then we can again linearize the network, right? If we twice the gamma, then the function will be twice. If we add two gammas, like a gamma 1 plus gamma 2, then the function will be added. So, and of course, this is a typical example of a joint equivalent machine. Right. So before stating the main theorem, I will explain how to obtain a joint equivalent map. One canonical method is to use a regular action of group G. Given any map, phi 0 from x to y, and apply a group action in this manner, like a Gz inverse phi 0 Gz. Act Gz inverse on data x and act Gz on output y. This type of action is sometimes called a regular action. And if you regard this group element itself as a parameter, this extended function, extended map phi x times g to y is by definition joint equivariant. Okay, this is a canonical method to obtain a joint equivalent map. And the nice thing is that if you have n joint equivalent maps, then the compositions of n equivalent map is again joint equivariant. So the joint equivariance property is suited with the function composition. So this property is nice to analyze a deep neural network or deep structure. Right. And finally, I don't use this property, but if the feature map is group equivariant, then we can say that its integration is also joint equivariant. So you can find a joint equivalence everywhere. And this is the main result. The first line is a recap of a joint equivalent machine. This is a linear combination of a joint equivariant feature map. And the Ridgelet transform is given by this form. This is somewhat simple because it takes the inner product of fx and the feature map. So it simply measures the similarity between fx and the feature map psi. And similar to the neural network case, this psi can be different from encoding function phi. So for encoding and decoding, we can use different feature maps as long as it satisfies some coupling condition. And the only assumption we need to verify is the irreducibility of representation. Let's define the group representation pi in this form. This form is again regular action, G inverse Fg. If this representation is irreducible, then if we substitute the Ridgelet transform to the place of unknown parameter distribution gamma, it reproduces the original function f up to constant c. It only depends on the choice of phi and psi. So it's independent of a function f to be approximated. So this first item is essentially the only assumption we need to verify. If you are lucky and you can find the irreducible representation of group G acting on L2 space, then you can automatically say the universality of this group equivalent machine M. And the nice thing is that the proof is very short. Only 1, 2, 3, 4, 5, 6, 7 lines. Very short. And we use Schur's lemma. Schur's lemma is a fundamental theorem in group representation theory, and it is a rephrasing of the irreducibility of a unitary representation. It's a bit technical, but if you have a bounded operator, bounded here means that continuous operator T on H, and if it commutes with the representation pi, I mean the pi T equal T pi, then this T has to be the constant multiple of identity. So it has to be a scalar. This is Schur's lemma. It sounds very technical, but in the proof, we take T as a composition M and R. And by using the joint equivariance and invariance of measures, we can straightforwardly show that the M and R commutes with pi. So according to the Schur's lemma, if the pi is the irreducible representation and M and R commutes with pi, then M and R has to be the constant multiple of identity. But this finishes the proof. M and R is C times identity. So R encodes the information function to the parameter space, and M decodes the information of function to the real domain, or in this case, function space from X to Y. Okay, very short. But the result is very strong. It covers a variety of examples. The first example is depth to fully connected network. In this setup, the group G is the affine group. Affine group is a semi-direct product of GL. GL is regular matrices, and RM is m-dimensional shift. And the group action on RM, the data domain, is given by an ordinary affine transformation, like G dot X is given by Lx plus T. And here L is matrix and T is a vector. So this is an ordinary affine group action. But on the other hand, you can also find the non-trivial dual group action on parameter domain. It is given by this weird-looking expression. And here L and T is same as the L and T in the group action on data domain. This is very weird, but it satisfies the joint group equivariant condition. I mean, if we act group G on data and the parameters simultaneously, then everything transformated, like X is transformated to map to Lx plus T, and A and B transform to L inverse transform, L inverse transpose A, and B will be B plus T transpose, and L inverse transform A. But after all, everything cancels out, and it reproduces the A dot X minus B. This is a trick. So this is a form of joint G invariance, but invariance is a subcase of equivariance. So now we see that these two actions, under these two actions, sigma A dot X minus B is joint group invariant. And in addition, there is a lemma. This is a non-trivial known fact, and the proof is not easy, but the regular action on L2 space, regular action of an affine group on L2 space is irreducible. This irreducibility is not trivial. You need more than 2 or 3 pages of proof. But anyway, we know this fact. So according to a general result, if you put the integration of a sigma a dot x minus b with respect to parameter as a neural network, and integration of a rho a dot x minus b with respect to data as a Ridgelet transformation, if we compose this, it reproduces the original function f. And in this case, we know the detailed structure of a neural network and the Ridgelet transform. We can exactly compute this constant. And it is given by the previous one I showed you before. Okay, this is a fully connected case. And yes, how to find the dual action? It's somewhat easy. Yeah. Just act a group G on X as usual, then find a nice AG and BG that satisfies AG dot X G minus BG equal A dot X minus B. If you are lucky, you can find a dual action. If it's impossible, you cannot find a dual action. So it is somewhat related to invariant theory in algebraic stuff. Okay. And for the depth n case, you can also find a group G, group actions on deep, fully connected feature map in a similar manner to the depth 2 case. In particular, for the parameter space, the dual action is not unique, but the simple case is given by this. This is the one that only acts on the bottom layer and the top layer. And it doesn't act in hidden layers. Still, you can see that under this action, deep map is group invariant again. So according to a general result, this is a Ridgelet transform for deep neural network. And if we substitute this to the weighting function of gamma of a deep neural network, you can reproduce the original function f. And of course, you can show the irreducibility of a group action on L2 space. And another non-trivial application is the universality of a depth n group convolution case. Of course, if the network is group convolution network, then it is already group equivariant in a classical sense. So according to a general result, you can show the universality directly. But you need to find a nice group representation pi that is irreducible. But instead here, we take a different approach. Here, our approach is turn a fully connected network to a group convolution network. Then I don't step into the detail, but you can also show the universality of deep group convolution network. And this formulation includes not only the standard G convolution, but also deep sets and the EN nets and blah, blah. And finally, unknown network that has a quadratic form inside a nonlinearity. So this network is a new network that is not known to be universal. So let the group G to be an affine group and X to be Rm again. So the G action on data is just given by a Lx plus T. And assume M to be the class of m-dimensional symmetric matrices with Lebesgue measure, blah, blah. And consider the feature map like this. This is almost similar to the fully connected network, but in addition to X transpose B plus C, it also has a quadratic term. So this feature map is not known to be universal before. But under this weird-looking group action, dual group action on parameters, you can again show the group invariance. So according to the general result, we can say that the integration of this quadratic neural network is again L2 universal. Maybe you can also find a cubic or more higher order version, I guess. So that's a non-trivial usage. Okay, so in summary, we introduce a joint group equivalence. It unifies shallow and universality theorem for shallow and deep neural network. And the essential technique was Schur's lemma. And it covers not only fully connected network, but the group convolution network and quadratic blah, blah. And in conclusion, the ultimate goal is to characterize the deep network solutions. And there is a Ridgelet transform. And, but classically, it is known only for depth to fully connected network. But if you use a group representation theory, particular group equivalent feature map, you can find the Ridgelet transform for a general network. Okay, that's the conclusion. Thank you very much.
So, question? Yeah.
For the multilayer case, do you have a nice way to compute this transform?
For
the multilayer case that you showed at the end, do you have a nice way to compute the transform? For instance, for the two-layer case, you had this theorem that said that.
Yeah, like this, right?
Yeah.
Yeah, of course, numerical integration of Ridgelet transform for deep case is computationally hard. Yeah, but theoretically, we can say that after the gradient descent, it converges to the Ridgelet transform because of the linearity.
But you would still need to impose a bunch of conditions to get some kind of uniqueness in the solutions and also.
Yeah, of course, we need to also additionally impose some regularization term.
I also have just a clarification question, because you mentioned that with the quadratic term, the universality hadn't been shown before, but you can always just set A to 0, and then, so I'm just wondering if you could clarify this point.
Oh, yeah. Maybe it's my guess, but the case when A equals 0 is measure 0. So,
I see. Okay, so something about the
maybe
integral.
it doesn't matter.
Okay.
Other question? Yeah, please.
It's unclear to me. So normally when we consider the integral the formulation, we consider the probability measure or signed measure to the parameters A and B and C. Okay. Here you consider the Lebesgue measure. So I'm wondering if we consider the probability measure, so the results will be significantly different.
Yeah, if the group invariance is important for showing the commutation property. Yeah. So if we consider weighting version, you need to inverse.
I see.
If you impose fx dx, then you need to impose f inverse x at somewhere.
I see. Okay.
Yeah. So as long as you have a density function, it's not a problem.
I see. In this case, do you need to consider about the gamma, the function? So it's still unclear to me is there is no constraint or some condition on the gamma, right? Normally, we need to ensure that the gamma is decaying and such that the integral is well.
Yeah, I don't care about the gamma because this is the image. This is inside the image space. Okay. As long as f is regular, maybe I believe that the image gamma is also regular. So, and the only the technical assumption we need to verify is that the L2 boundedness of M and R.
Okay,
So the image space of R is not much a problem.
I see. Okay, thanks.
Other question? I have a related question. So you use a Rubik measure for the X.
Yeah.
So then if you change the measures, then can you say something about irreducibility of some group? What we should do is just you multiply fx inverse, then you apply this result.
If you impose some inverse factor that cancel out the weighting, it works.
Is this the only way, or can we directly show the irreducibility?
Yeah, if you may, of course it depends. Maybe sometimes this continuity breaks if you impose a very strange weight. Yeah, that could be possible.
But maybe like a Gaussian.
Maybe Gaussian works.
Okay.
But it of course depends on the choice of X. If we consider like a sphere, then there is no such kind of Gaussian stuff. Or if you consider a graph, then there is no such kind of stuff like a Gaussian.
Okay. Yeah. So, other questions? Okay, so no? Okay, so is there some online? So, okay, so if no questions, so let's thank the speaker again.
Thank you very much.
Hello, everyone. It's a pleasure to be here in Tokyo. So I'll be talking a little bit about diffusion models. And in this talk, the results aren't really important. So the point of the talk is more just to think a little bit more carefully about what diffusion models are doing. So with that said, I would welcome any questions that you have. Okay, so this is some joint work with some collaborators at Yale. Alkis, who's a postdoc, Ane, who's a PhD student, and Omar, who's a assistant professor. Okay, so just to fix some notation, let me give some background on diffusion models. Unfortunately, I didn't put much general background on diffusion models. I'm kind of assuming that you know some of the basics. But okay, so the diffusion model, what we want to do is we want to draw samples from some data distribution, which I'll call P data. But I'll also call this P0, where 0 is the time index, because we're going to soon evolve this along a diffusion process. And the diffusion process is the Ornstein-Uhlenbeck process. So in practice, there's different kind of time rescalings you can do. But for the sake of mathematics, we just use the simplest scaling. So we just use this Ornstein-Uhlenbeck process. So we start with the data distribution, which a running example might be you want to generate images. So P data is your distribution over images. And then you take each image and you evolve it by this diffusion to produce a noisier image. And let's say that xt is the output of this process at time t, and pt is going to be its law. Now, what diffusion models are based off is that you can actually reverse this SDE in time, and you end up with this so-called reverse process. And this reverse process actually has a closed form expression as this SDE. So in this reverse SDE, what you do is you change the sign of the drift. So negative xt becomes positive xt. But then we add another term to the drift in order to make sure that this time reversal is correct. And this extra term that you have to add is the gradient of the log density, which is called the score function. Okay, so the idea behind using these diffusion models to do generative modeling is if I can somehow implement this reverse process, then this reverse process, it should actually go the other way. It should take me from noise into sensible images. So we want to implement this reverse process. But when you look at this reverse process, the thing that you need to do is you need to be able to implement this score function term. Now, one of the main innovations of diffusion models is this idea of score matching. So score matching is a way of formulating a regression objective, which lets you learn the score function from data. So the way this works is that we have this score matching objective, which turns out to look like this. It's not so important, the specific expression of this for the talk. So I will abbreviate this throughout as SM sub t. So SM stands for score matching. This is the objective at time t. it takes in a certain like function st, and also a data point x0, and then it evaluates to this expression. So this is the gradient log density of the transition density of the OU process, but again, not so important. And the important thing is that if I take this score matching objective and average this over the data distribution, then the minimizer of this over all functions st is actually the true score function, grad log pt. So the important part about score matching is that we can form an empirical version of this, which is you replace this expectation over the data distribution with a bunch of samples from your database. So this would be like I have a big database of images like CFAR10 or something, and I take these and form this empirical objective and train. Now I need to optimize over st to learn the score function. And in practice, we optimize over some class of score functions, for instance, based on your neural network architecture. So this would give you the learning objective. Okay, and then this is all the training process. And then to actually generate images, what you do is you take these estimated score functions, s hat t, and you just take the reverse process and you replace that score term with the learned score. And then you also discretize the SDE. And then you run this. And you run this reverse SDE starting from the Gaussian distribution, which is the stationary distribution of the forward diffusion. And you run this for time t, like backwards, and then you end up with samples which are hopefully close to the data distribution. So you start with noise, and then you generate images. OK, so let me tell you the kind of basic results in this direction about what these models do. So these are called denoising diffusion models, or DDPM, in the machine learning literature, which stands for denoising diffusion probabilistic modeling. And the theorem is the following. So diffusion models can actually output samples from a distribution P0 hat, which is epsilon close in total variation distance to the true data distribution. Okay, so it can actually output samples that are close to the distribution that we desire. The number of steps that it takes to generate is only scaling polynomially in these parameters, d, l, and 1 over epsilon. And these are the assumptions. So first of all, this first bullet point are the assumptions on the data. So the first assumption is that the score functions should be Lipschitz along the diffusion process. So actually, this assumption can be removed, and I will do so in just a second. But for now, just say that the score functions are Lipschitz, and then also some mild second moment bound. Okay, so these are pretty mild assumptions on the data distribution. And then the second assumption is that the score functions are actually learned accurately. Okay, so if you have a total error for the score functions, which is like the squared L2 error is epsilon star squared, this translates into epsilon total variation error for the sampling. Now this first bullet point, the assumptions on the data, this assumption is actually quite mild. And the reason why it's mild is because it doesn't assume anything such as log concavity of the data distribution. So what's typical in the literature on sampling is that if I have a very multimodal distribution, then that's very hard to sample from, because local samplers will take exponentially long amounts of time to jump between the modes and so on. So typically, to get sampling guarantees, you need strong assumptions on the data distribution. But here, these assumptions do not require any of this. And that's some intuition is that these denoising diffusions, because they go forward along this diffusion, they have some kind of annealing process built into them. Okay, I also mentioned that this Lipschitz score assumption, so this is also too strong, because if you think about, if you imagine that your initial data distribution is supported on a low-dimensional manifold, which we might expect natural images to behave like this, then the score function at time 0 would not even exist, because it's a lower dimensional distribution. And then that means the score function for small times has to blow up. But in fact, you don't need the Lipschitz score at all, because what you can do is do some early stopping. So you could stop the diffusion very early at some time tau. Okay, and You can make tau extremely small because the overall complexity only depends logarithmically on 1 over tau. So with that, with the regularization built into the diffusion and this early stopping procedure, then you can handle pretty much arbitrary data distributions. So this was a work I had with some collaborators back in 2023, and the title of our paper was "Sampling is as easy as learning the score," because that was the main message of the paper. It's like, provided you can learn the score functions, which is the key question, right? We don't know how well these neural networks do manage to learn the score function, but if you can learn the score function, then you can sample from essentially arbitrary data distributions. Okay, and I guess this the name of the paper became kind of catchy in the literature. And there's also some concurrent work and many follow-up works after this. So this is kind of the starting point of this talk. What I want to do in this talk is explore like what this result is saying in a little bit more detail. Okay, so as I said, the point of this talk is to just get you to think a little bit more clearly about what diffusion models are doing. So I thought we should play a little game. So in this game, I'm going to list some tasks, and I want you to raise your hand if you think this task is well-defined and makes sense. So by a well-defined task, I mean like the task should have some clearly defined answer. There should be like a measure of how like difficult this task is. Okay, so the first task I'd like to ask if it makes sense or not is the following. Okay, the information you're given is that you're able to evaluate the density of the distribution P0 at various points. And given access to density evaluations, your goal is to output a sample from this distribution. So who thinks that this task makes sense? Okay, I see most of you raising your hands. So yes, this task makes perfect sense. In fact, this is what's traditionally thought of as Markov chain Monte Carlo. So when you do like Bayesian inference or something, what you can do is you can evaluate the posterior distribution. You can evaluate the posterior density, and based on that information, you have to design a sampler from the posterior. So that's fine. Now, here's the second task. Okay, you start with samples from this distribution P0. And now, given these samples from P0, you have to learn the score functions along this diffusion process. So who thinks this task makes sense? Okay, I actually see some less hands, but the answer here is still like it makes sense. This is actually just standard statistical learning theory, right? You get some samples from a distribution, you have to learn something about the distribution. So there's been some work in this direction as well. Yes. I guess like maybe when I'm done with this slide, you'll see why I'm posing this question. Okay, so the third task is, given access to evaluations of the score function along the diffusion, I want to be able to output a sample from P0. Okay, so this is the information I'm given, and again, the goal is to output a sample from P0. Does this task make sense? Okay, so the answer is yes, this is exactly the theorem that I just showed you. The previous theorem said like, okay, given access to accurate score evaluations along the diffusion, this is how many times you need to, how many steps you need to run the diffusion in order to output a sampler. So this is a well-defined task, and one open question here is actually like, is there a lower bound for this task? Like, what's the minimum number of score function evaluations along the diffusion process that you need? Okay, so now we come to point 4, which is what's traditionally thought of as generative modeling. Okay, you're given existing samples from a distribution P0. The goal is to generate new samples from P0. Okay, like I train on CFAR10, now I want to generate pictures of new animals or something. So who thinks this task makes sense? Okay, so now what I want to argue in this task, in this talk, is that no, this is actually nonsense. There's no way to make sense of this task. And the reason why is that if you could really generate genuinely new samples, this would violate everything about information theory. So just imagine like if if you start off with n samples from some distribution and then you need to solve some learning task, if you could somehow like take those n samples, transform it into even just n plus 1 samples, like one extra sample. You cannot use, like with these n plus 1 samples, you still cannot do better than your original n samples because you did not gain any new information anywhere. And what goes wrong is that the new samples that you generate are not statistically independent of your original samples. So in that sense, it doesn't really make sense to talk about generating new samples. So although like generative modeling is traditionally thought of as this task over here, it's actually not a well-defined question. So then the question is, what is generative modeling actually doing? And that brings me to this fifth and final task, which is given existing samples from P0, the task is going to be to learn a sampler for P0. So in this talk, I'll like make precise what it means to learn a sampler from P0, but this is actually going to turn out to be the right way to formalize what generative modeling is doing. Okay, so the message that I'm heading towards is that what generative modeling is really doing is also known as distribution learning. And distribution learning is just a classical question in statistics. So let's talk a little bit about distribution learning. So in distribution learning, what you have is you have some class of distributions, script P, which is known to you. Okay, and you know that the true distribution, which is little p, belongs to this class of distributions, and I get a bunch of, say, IID samples from this unknown distribution. And the goal is to learn what this little p is. Okay, so that's distribution learning. But actually, like, if you really think about what it means to do distribution learning in practice, you have to be a little bit more precise about this, because you have to talk about how you represent the distribution. So what is the form of the output that you're going to give to me? So there's various ways to represent a distribution. Maybe the simplest one is if this class of distributions I'm trying to learn is indexed by a finite dimensional parameter, then I could just output this parameter. Right? So like if I want to learn a Gaussian, it suffices to just output its mean and covariance, because that completely specifies the distribution. So in this finite dimensional setting, we call this parameter recovery. Another form of distribution learning, when you don't have this finite dimensional setup, is known as density estimation, which is another very classical form of distribution learning. So in this case, the goal is to output what's called an evaluator. So what is an evaluator? It's a learned function p hat, such that to this learned function, I could input any point x, and p hat of x is going to be some estimator of the density, the probability density of p at x. Okay, so I really just want to estimate the density, the unknown density pointwise. And this is what you might normally think of as distribution learning. Now I'm going to tell you one more form of distribution learning, which might be a little bit different from what you've seen before. And here, the goal is to output what's called a generator. So what is a generator? A generator is a function, a learned function, which I'll call g hat. Okay, and it's going to map from, let's say, the unit interval to RD. And what this generator does is it takes in a uniform random variable, which you think of as a random seed, and it will output a sample, okay, such that if I look at the law of the output of this generator conditioned on the data that I use to learn the generator, then I want the law of the output of the generator to be approximately equal to the true distribution P. Okay, it's important that I condition on the data, because like one thing I could do is I get a bunch of data points and my generator just outputs one of the data points that you gave me. This is not doing any non-trivial learning. So in order to do non-trivial learning, you condition on the data you've seen, and then you want the law of the output of this generator to be approximately P. And this last form of distribution learning, this is actually the form in which diffusion models are actually doing distribution learning. Okay, because what a diffusion model, like after you have trained all the score functions, okay, I could give you this pile of trained score functions that corresponds to this function g hat, because then what you do is you generate a new random seed which will run this like reverse process, and then the output of that diffusion model will be a sample from your distribution P. Okay, so although like this might be a little bit harder to wrap your head around at first, it's actually a more useful definition than density estimation, because like if I have an estimator of your density, what do you actually do with the density estimate, especially if you're in high dimensions? Like, can you use this density estimator to like build confidence regions or any other like useful task? Not really, unless your density estimator is really simple. Actually, my advisor, Philippe Rigolet, he used to work a lot on density estimation, and then he stopped working on density estimation. And the reason why he stopped working on density estimation is he realized that no one actually does anything except histograms for density estimation, like in practice, because what do you actually do with this complicated object? But if you have this, like a generator implicitly contains within an algorithm for producing your samples, which is much more useful. You could use these samples to do whatever you want. Now, I gave you these different forms of distribution learning, but I want to make one more point, which is that the difference between these forms of distribution learning is purely a computational question. Okay, information theoretically, all three tasks are the same. So the reason why is, imagine that you have unlimited computational budget. Then if I could solve density estimation, then I could certainly output samples, right? Because I take this density estimate that I have, and I do something like rejection sampling or whatever. However, like this could take a very long time to generate a sample. And vice versa, if I have learned a sampler, what I could do is I could just call this sampler like infinitely many times, generate infinitely many like new samples, and then like fit a density estimate to that. And then I would solve density estimation. So if I don't have any computational constraints, these are the same task information theoretically, which means that the same information theoretic lower bound applies to both. So in statistics, we have the idea of like density estimation lower bounds, right? Like the best you could do minimax over some Holder class of densities or whatnot. That same information theoretic lower bound would apply for the task of learning a sampler, because information theoretic lower bounds don't care about computation. What I'm going to talk about here is about computational complexity, and that's where these two tasks start to differ. Right, that's what I just said. Okay, and that means like if I really want to understand the difference between these two tasks, I need to talk about genuine computational lower bounds. Like I need to start with assumptions about complexity theory in order to really say something. Okay, now let me take the theorem that I already showed you and just reformulate this in this new language of distribution learning. So what the previous theorem said is summarized as follows. You can take almost any like realistic family of distributions. Remember, like we had very minimal data distribution assumptions. Then first of all, like remember that the theorem said that if I have a accuracy guarantee for learning the score functions, this translates to a TV guarantee for learning the distribution, right? So what this says is that the sample complexity of learning a sampler for this family is at most the sample complexity of learning the score functions. Okay, so it reduces the sample complexity of this task to the score function task, which is a regression task, and you can understand that pretty clearly. And then moreover, like because the number of iterations that you need to run this diffusion model is a polynomial, the computational complexity is also like not much harder than learning the computational complexity of like learning these score functions. So if I summarize this by another slogan, because in machine learning we love slogans, we could say that learning a sampler, this particular form of distribution learning, is as easy as learning the scores. So this was all prior work. Oh, and okay, let me also give some examples of this idea of learning a sampler. So there have been many papers that study the statistical rates of learning the score functions along the diffusion. This is obviously a very relevant question because we want to know how well diffusion models should do, and including, for instance, some work here at RIKEN on learning these score functions. And now they've established, like, for instance, that DDPM can get minimax optimal rates for distribution learning. So here, what it means is like minimax optimal. So this result is like in the sense of learning a sampler, right? You learn the score functions well. Therefore, by the previous theorem, you can learn the distribution well in the sense of learning a sampler. Okay, and the minimax lower bound is purely information theoretic, so it doesn't care in what representation of the distribution you output. And there's also been some algorithmic results for other classes of distributions, for instance, like mixtures of Gaussians. Okay, so that was kind of the prior work, which is over on the left side. The left side says that this idea of generating samples is reduced to the problem of score estimation. And now the new work that I want to talk about is going to relate these other two notions of distribution learning, namely density estimation and parameter estimation, also to score estimation. That's kind of the point of this talk. All right, so here's the outline. So all of this really stems from some very simple observation, this identity that I'll show you. And then this identity, if you think about it, is going to have various implications, which I'll go through. Okay, but what is this identity? So just recalling the notation, remember I used this SM for the score matching objective. So just recall that the true score function is the minimizer of the expected score matching objective. And what we do is we fit on the empirical version of this objective. And now this is the key identity, which is that the negative log density of your data distribution at any point x0 turns out to equal the following thing. It equals the integral over time of this score matching term, SMT, okay, evaluated at the true score functions, plus some explicit constant, CDT, which I wrote here, but it's just some explicit thing that you could put in by hand, plus something that decays exponentially with time, which means that if I take the time large enough, then you could essentially ignore this. Okay, and various versions of this identity have kind of been known in the literature before, but what it says is that the negative log likelihood of your model is like closely related to this score matching objective. So let's see what we could say using this one identity. So first, let's talk about the setting of parameter recovery, which we said was like when your distribution family is indexed by a finite dimensional parameter. Okay, so we're in this parametric setup, and let's say our data is distributed from a true parameter, theta star. So there's been some works studying parameter estimation using score matching. This is just trying to understand like how effective of a statistical technique is score matching. So this prior paper is one of the closest to what we did, but they study a different form of score matching, which is known as implicit score matching. So implicit score matching, there's no diffusion process involved. It's instead deriving a score matching objective using some integration by parts. Okay, so this score matching objective is defined as the argument of this following objective, which you derive via integration by parts. And they studied this estimator, and what they showed is that the implicit score matching estimator is asymptotically normal, and the asymptotic variance is some matrix, which I'll call sigma ISM. Okay, moreover, what they were able to do is, under the assumption that P satisfies what's called a restricted Poincare inequality, that this asymptotic variance can be related to the asymptotic variance of the MLE. And the asymptotic variance of the MLE is well known to be the inverse of the Fisher information and is optimal in various senses. Okay, so they're saying like under this assumption, we can say that the implicit score matching estimator is not too much worse than the MLE because we could relate these asymptotic variances. The trouble with this is that this is actually a very strong assumption on the data distribution. In particular, like let's say I want to learn a mixture of Gaussians or something like that. It will have a very poor Poincare constant, and therefore the implicit score matching estimator will be provably much, much, much worse than the MLE, like exponential in the dimension worse than the MLE. Okay, so this is saying that this basic version of the score matching, it sometimes works, but if your data distribution is complicated, then it will be statistically very inefficient. Now, the reason why this is interesting is this Poincare inequality I mentioned, it's actually more classically related to the mixing time of Markov chains. Okay, this inequality is actually the inverse of the spectral gap of a Markov chain. So their work is connecting two different things, which is how fast do I have mixing for like Markov chains that target this distribution versus like the statistical efficiency of learning the parameter in this family of distributions. So this analogy, if you push it a little bit more, they had a follow-up work which said, okay, the previous work said that score matching could be very inefficient if I use score matching associated with a local Markov chain. But if I have data which is, say, a mixture of Gaussians, there's actually faster mixing diffusions. Like you can do some like simulated tempering and so on. So if you do score matching along these other diffusions, then you can actually get polynomial sample complexity for mixtures of Gaussians. So by changing the diffusion, you get faster mixing and better statistical efficiency. Now, like what I'm interested in is what about score matching along the diffusion model, which we know is will always sample fast. So we can define a notion of like a DDPM estimator, which is we simply like take the parameter theta, which minimizes this score matching objective, where this score matching is now done along the diffusion model. Okay, so this is a natural idea for a DDPM parameter estimator. But actually, like if you remember this little identity that I showed a couple of slides ago, if I take the log density evaluated at a point, it's exactly this integral of the score matching objective plus this constant, which doesn't depend on anything, so it doesn't matter for the optimization, plus something small that we can ignore. So this identity directly tells you that minimizing this objective is basically equivalent to maximizing the log likelihood, which says that this DDPM estimator is essentially the same thing as the MLE. So what you can show is that as long as like the times grow sufficiently fast, you just need it to grow faster than 1/2 log n, then the DDPM estimator that I just wrote down is going to be asymptotically normal with a covariance matrix that's exactly the covariance matrix of the MLE. There's no constant factor or anything, it's just exactly the MLE. So what this says is that if you care about parameter estimation, then it's as easy as properly learning the scores. What I mean by properly learning the scores is that if you look at this objective up here, what's important here is that all of the score functions that I'm using are consistent for a single value of the parameter theta. Okay, so in order to do parameter estimation, I need to learn a bunch of scores which correspond to the same parameter value theta. But if I can solve that task, that's the same thing as doing the MLE. Okay, so next let's turn to the implication of this identity for density estimation. So here's the identity again. The negative log likelihood is the integral of the score matching objective. Now this gives you a direct estimator for the density itself. If I want to estimate minus log density at x0, why don't I just take this integral and instead of the true score, which I do not know, what if I just plug in my learned score functions here? Okay, and then I just keep this constant here because it's very explicit. I know what it is, and then I just drop this last term because it should be small. So this is a reasonable density estimator. And now here's a theorem which is supposed to mimic the very first theorem I showed you. Okay, so the density estimator that I just showed you, it achieves a density estimation guarantee in the following sense. The expectation of the absolute value of the log differences, the difference of the log of the densities, is at most epsilon. Okay, it runs in polynomial time, and this assumption is the same as what we saw before. There's a slight difference in the second assumption because the second assumption, Like before, we only needed the score functions to be learned to error epsilon squared, but now we need them to be learned to slightly better accuracy. Like there's a factor of the dimension that shows up. Okay, so the difference between the previous theorem is like the second bullet point and also the first, the notion of error. And also like here, we're trying to do density estimation rather than learning a sampler. Okay, and just as before, you can remove this Lipschitz score assumption by some early stopping. Here, the dependence on 1/tau is also worse, but that turns out to not be an issue for applications. Okay, and the density estimator that I showed you, so remember, this is the density estimator that I'm proposing. You take your learned scores and you plug them into this. Well, then P0 hat is always going to be the exponential of something, so it's always non-negative. So you always output a non-negative function, but it might not integrate to 1. It's kind of improper density estimation. And this kind of guarantee that I'm saying on the expectation of the absolute value of the logs, it implies that our density estimator will be close in a multiplicative sense to the true density on most of space. That's how you can kind of interpret this guarantee. So what can you do with something like this? Okay, so we call this notion of density estimation pack density estimation in analogy to pack learning. So pack is like probably approximately correct learning, just because like it resembles the kind of guarantees there. But you can view this as a weak form of density estimation. Like typically density estimation, you might care about the L2 norm of the difference of your estimate and the true density or something like that. This is, I guess the notion of error is slightly different, but it's roughly doing density estimation. So here's like an example. Consider this non-parametric class. This is going to be a holder densities on the interval -1 to 1. Okay, and these densities are going to be S times differentiable. They have some uniform lower bound on the density on this interval. And then L is going to be the size of the holder ball, like the bounds on the derivatives. Okay, so this is a standard like non-parametric density class. Now this is one of the classes that was studied in this paper, for instance, which also came out of Yale. And what they were studying is like, what is the rate of score estimation in this class? And what they were able to show is like some rates of estimation for score estimation leading to a minimax optimal sampler. Remember, this is distribution learning in the sense of learning a sampler. But using this density estimator that I just showed you, you can take their same score estimator and also argue that you can get a nearly minimax density estimator. Okay, so there's a density estimator based on this DDPM score matching such that if I consider like the L1 risk for the densities, then you get this minimax rate up to a log factor. Okay, and you can also do this for other examples, but the point is like every time in the literature that you saw a result on learning the score functions, basically implied that you could learn a sampler, but now this result is saying you can also do density estimation. Yes?
So the first is, this is still using that log here, right? Is there anything else involved? Or?
Some hacks, I guess.
But it is, okay. My other question was, if you mind going back to the previous theorem. So was there prior work that was able to get a similar result, but it had like an exponential dependence on dimension? Or was there no prior work of this type?
To do density estimation via score matching?
Yeah.
At least I'm not aware of any.
Because the naive way, of course, is you could just form histograms.
Yes, yeah.
So I was just wondering if one of the general messages that you're trying to tell us via this identity is that it avoids Poincare and log Sobolev inequalities in general, in many cases where it seemed they were used before, because that was the case for Andre's result that you mentioned.
Yeah, so it's true that like because DDPM could be used to learn a sampler and then you could generate samples and form a histogram, the thing is like density estimation given samples usually requires like exponentially many samples because of the recursive dimensionality. This is giving a direct way of doing density estimation directly from the learned score functions. Yeah.
If I can ask one third question, because I'm still trying to figure out how you circumvent all these difficulties in an intuitive sense. The fact that you're improper, that it's not a probability density, is that Is that something you don't know how to fix?
Yeah, that's just because like I mean, we're just trying to translate this identity into an estimator, and the natural thing it gives you does not necessarily like integrate to 1. And enforcing that it integrates to 1, we have no idea how to do this in a computationally efficient way. Yeah, remember, like all of this, like the important part is the computational complexity, because if you don't care about that, then it's the same thing as learning a sampler. Okay, and then the final thing I want to say is like, so all of this says that if you could do score matching, then you can solve these tasks of like parameter recovery and density estimation. So if you can solve more tasks, that actually leaves you more vulnerable to lower bounds. So now I want to ask, like, can we actually get computational lower bounds against score matching? Okay, so the first comment about this is that we have to be careful, because, as I said, the distinction between these tasks is purely at a computational level. So if you have any information theoretic lower bound framework for proving lower bounds, that includes like minimax lower bounds or statistical query lower bounds or whatever, like these methods would apply equally well to both kinds of tasks. So what I'm after is like, can we actually get lower bounds from computational complexity? Okay, I start with a complexity theoretic assumption that a certain task cannot be done unless the complexity hierarchy collapses. And based on this assumption, can we show that it's actually impossible to do score estimation? And the way that the assumption we're going to base this off of is a cryptographic hardness. Okay, we're going to argue that solving a certain task is as hard as breaking a crypto system. So because we're basing a crypto system on this task, that means like we better be pretty sure about its security. So either we've like broken this crypto system, and then we have to like rethink cryptography, or this gives like powerful evidence of the hardness of something. And now like cryptographic hardness has been proven for density estimation, recently for mixtures of Gaussians. I guess I'll talk about this in a few slides, but the question is like, okay, we know that some density estimation tasks are cryptographically hard, and we've also reduced density estimation to score estimation in some sense. Can we then use this reduction to say that score estimation will also be cryptographically hard in some cases? Okay, let me also mention a fascinating open question along these lines, which is, can you actually get cryptographic hardness for learning a sampler? This seems pretty difficult to me, so I'm happy to talk about this afterwards. But basically, there's nothing known about cryptographic hardness for learning a sampler. So, okay, maybe I'll say like we have these two different forms of distribution learning, like density estimation and learning a sampler. Okay, for density estimation, in some cases, we know it's hard. For learning a sampler, it's unclear right now. We don't actually have lower bounds on this. However, diffusion models, they do score matching, and score matching can do both of these. So diffusion models, like we can get lower bounds through either route. Okay, so cryptographic hardness for diffusion models has been considered in this prior work by Min-Jae Song. And what he showed is that it's hard to learn the score functions for Gaussian mixtures with many components and high dimensions. But this was like using a very tailored argument specific to these like Gaussian score functions and diffusion models. What our reductions let us do is now we have this kind of general blueprint for how to show cryptographic lower bounds against score estimation. What you do is you just check that the family of distributions you claim is hard will satisfy the conditions of our reduction, which is very, very mild. And then you just need to show that this density estimation task that we claimed you can do is cryptographically hard. It can solve a cryptographic task. And the conclusion of this is that learning the score is actually as hard as doing density estimation, which can be hard. So we can recover Min-Jae's result using this framework. So here's a result, which is that for any epsilon, it's cryptographically hard to learn the score functions of mixtures of Gaussians with up to like d to the epsilon components in dimension d. Okay, so if your Gaussian mixture has a number of components which is growing with the dimension, and you try to learn the score function of this should be computationally hard, assuming that cryptography works. And this is kind of how such a statement would be proven. It's through this chain of reductions. So like what we argued in our work is that if you can do score estimation, then you can do density estimation in this way. Now, like density estimation, there's this prior work that defined this problem called continuous learning with errors. And they said, like, if you can do density estimation, then you can solve this continuous learning with errors problem. This continuous learning with errors problem is a continuous version of the learning with error problems. And in this paper, they showed that solving CLWE lets you solve LWE. And then the reason why LWE was interesting is because in classic work on cryptography, they showed that solving LWE is as hard as solving certain like worst case lattice problems. And finally, the reason why these lattice problems are interesting is because they've been used as the basis for designing cryptographic protocols, which are thought to be secure even against quantum computers. So the upshot of all of this is that if you could solve this Gaussian mixture score learning task, then you would be able to break our most promising candidate for post-quantum cryptography. So therefore, like, we think that it's pretty hard to learn score functions for mixtures of Gaussians. You cannot do anything. You cannot do everything with diffusion models. All right, so that's the summary of this work. Is we relate score estimation to these two forms of distribution learning. Okay, thank you for your attention.
So questions? Yeah.
Because there are no questions, so I ask maybe a bit naive question. So in some cases, so learning the distribution and also learning the score, you mentioned that sometimes they are the same in terms of the statistical efficiency, right? But there is a computational gap. So I'm wondering for what kind of the distribution they are easy, and then there is no computational difference. So for example, normally for the density estimation, we are to assume that, okay, the density function is for example smooth enough. Okay, these are easy to learn, both statistically and also computationally. So I'm wondering what kinds of the function or density function we can learn, for the computational set.
So you're asking between a separation between density estimation and score estimation?
Yes, exactly.
So there was a prior work which gave an example in which it's actually easier to learn the parameter. Oh, sorry, that's for parameter recovery. Well, like, I guess what our work is saying is that density estimation should always be easier than score estimation.
Yes.
As for example where score estimation is genuinely harder.
But I guess for some very simple density functions, there is no separation, right? For example, if we to learn a uniform distribution, I guess,
Yeah, I guess I don't have an example where score estimation is genuinely harder than density estimation.
Okay.
Yeah.
Okay, thanks.
Related to his question, I think you can run when the support of distribution is sparse, you can run DDPM. You can still run a DDPM, but the density estimation is difficult.
When the support is sparse?
Yeah, like a 3-dimension distribution embedded in a super high dimension space. Am I correct?
Okay, so maybe what you're actually asking about is whether there's a separation between these two tasks. Yeah, so I think there are some examples which show that there are separations, but I'm not sure of very natural examples that show a separation between generation and density estimation. So what I was saying in the last part of the talk is that if you start off with a cryptographic assumption, you can show that this is hard, but maybe it's actually still easy to do sample generation. we do not actually have computational lower bounds against sample generation. And like more broadly, like thinking about the differences between these two tasks is kind of interesting.
I have a comment on the sparse case. The sparse case, if you're thinking of approximation in the soup norm. So if you're doing something like soup norm, then you have to estimate. For instance, it guarantees a lot for Lipschitz score function, which allows for a function of exponentially many of these little spikes. And if you were doing estimation in the soup norm sense, then it would be hard. But since all of these guarantees are they're in an expect guarantee. So I think that removes a lot of the intuitive hard cases. I don't know if that's relevant. I think it's all. I'm just saying, because classically, if you open a classical book on density estimation, sometimes it has uniform guarantees.
Yeah, that's true. We do not know how to get such guarantees using DDPM score estimation.
And apparently this was off. So for the gap between density estimation and generation, can't you, I mean, is it useful to think about any case where the log partition function is hard to compute? Because that's a natural way to get rid of that like 99% probability mass issue also. But I guess you were saying that you don't know of any such cases that are genuinely hard to sample?
Right. I do remember having various conversations with people about this. Like some people suggested like spin glasses or something like that, where like the typical samples from those distributions will all have like around the same energy, in which case density estimation should be easy, but then it's still hard to sample from this. That's like one direction, I guess. Yeah, I think if you try, you could definitely find various like separations between these. Yeah, but I guess maybe one meta point is that, as I said, I think that generation is a task that makes more sense for our modern applications of distribution learning. And all of the current like lower bounds are really aimed at this. So the fact that we don't really know how to do computational lower bounds for generation is something that I think we should study, because yeah, that generation is maybe an easier task than density estimation, but still like useful, maybe more useful.
Other questions? So maybe my question does not get a point. Maybe so. Can we say anything on the total computations, including the estimation and generations? Okay, so you get like a samplers. So then maybe there is some trade-off of estimating the before sampling, and when you want to generate the sample, so you need additional computation complexity. So do you say something on the total computational complexities? So.
You mean from the like upper bound perspective or the lower bound, or
maybe upper bound? Yeah. So if you spend more computation for estimating or preparing the generators, maybe so we only need a very less computation for generations, maybe vice versa.
I guess like there's not really been a trade-off for diffusion models, because the amount of time you need to learn the scores just depends on the like accuracy that you need to sample to within, mm-hmm. And then the generation after that was just polynomial time. Yeah, for lower bounds though, like you would want to specify that both the training and the generation are both polynomial time. And then you want to say that this task is not possible.
Other questions? No. Oh, okay. So no questions? So no online question. Okay, so then let's thank the speaker again. Thank you very much.
I'll talk about two different things, honestly. I try to vaguely connect them, but they're not that connected at the end of the day. So, but here's the vague connection. They do both involve something that I've been working on a lot, which is just like, why does gradient descent work? And it's kind of two different settings. One is, so that's roughly still also the goal of this talk, to demystify gradient descent in a setting maybe we have settings that we haven't looked at a lot recently. One is in the context of some sort of test time inference, a very simple kind. So that's going to be the first part. The second part is kind of a very more classical problem that somehow we haven't been able to analyze until now. And so the first part kind of involves just a single gradient step, but the second part is like a full trajectory analysis. And I'll kind of get into each separately. So that's high level. So yeah, the motivation for the first part, which is joint work with Emrola, Alperen, and Zhuchen, and Samet at Michigan, and Marco at ISTA. So the motivation for this is kind of like this interest the last year and a half about like these quote-unquote test time inference models or reasoning models. You know, of course, we saw a lot of models like this past year. More recently, you know, this was supposed to be announced today, I think, or yesterday. It wasn't, but so somehow the idea that there is a new kind of test time inference as a new paradigm in scaling, and so we wanted to just analyze something very simple in this setting, so this is related to in-context learning. And then I'll kind of mention, and in particular, very specific kind of it. So this is kind of the task that we look at. So in context learning is like this property that these language models have, where you know, you give it some demonstrations, right? And then they're able to kind of like, if you now give it a new input demonstration, the models are able to kind of predict this new thing, right? And so the idea is that if you give this entire list, including the question mark, the model is supposed to give you like the new output, right? So that is the task. And this is kind of an interesting task to measure the generalization capabilities of these models. It's kind of an interesting setup to do this in. So because this is going to be a theory talk, this also make it mathematically a little bit more clear. So imagine you have some input-output pairs like xi, yi. So you see a bunch of them at kind of at the end you see the input, but you're kind of missing the output. So you have 0 there, right? And so one particular challenge where this is interesting is like this ARC challenge, where you know during pre-training you show some tasks, right? For example, pathfinding, growth, gravity, and so on. But then at test time, so again, when I say you give them some tasks, for all of these tasks, you're given demonstrations of these tasks, right? Like again, like in context learning format, essentially. And then at test time, you see a different task that maybe it was not in the training data. And again, you see demonstrations, right? And so the question is like, if you've seen only this stuff during training, can you have models that do well at test time with slightly different tasks, essentially? And you know, and the answer was that well, the models at the time did not do so well, right? So you know, if you look at best humans, they're actually pretty good. Average humans, not so much actually. But then you know, like the Llama models, the free versions, were really not even close to the average human. So one idea, and this was a challenge, you know, eventually actually OpenAI, I think of all three actually did very well on these stuff, but they spent a lot of compute. It was very expensive. But if you look at the second and third prize winners in these challenges, one of the ideas that was very effective was this idea of test time training, right? And I'll show you how effective it was in practice. So, but what is test time training? So, test time training is this idea of like, you know, out of like my test data, I create some fake label data which I use to fine tune the model. So it's kind of like some sort of fine tuning. So here, you know, again, like I create some fake test time data where I literally fine tune the model, right? So in this case, you can see that this is kind of easy to do because you have demonstrations, right? So what you can do is just delete the last one because I don't know the answer to this. I cannot cheat. But I can delete the last one and then, you know, just remove this, right? And use this as like a test time training data. And I just fine tune the model based on this test time data, right? So, this idea ended up being really effective. Again, like if you look at the second and third prize winners, basically the biggest jump in performance was due to this test time chaining idea. And again, the way you do this is just run gradient descent when you do fine tuning, right, or stochastic gradient descent. Now, and if you do this and you do it with one or basically a few iterations, already you get a significant jump. This second and third prize winners actually did better than this by adding more bells and whistles. They were actually able to match the average human, but already you got quite a bit of jump by just doing a little bit of test time training. In fact, as I mentioned, like in doing a few steps or sometimes even one step of gradient descent on this test time objective was good enough to improve performance, right? And so that's the thing that we want to demystify in some sense. Why is it that a few steps or maybe even one step of gradient descent is so effective at test time, right? And so that is kind of the first part. So if you want to do theory, we need kind of a little bit to make some modeling assumptions. So for the architecture, we're going to use a very simplified architecture. This actually kind of well-studied architecture in the context of in-context learning by itself without test time training. So that's why we picked this. And this is the traditional kind of self-attention model. You have your input tokens. You pass it through these query key value matrices. You get the query key values. Typically, what you would do here, you would pass it through softmax attention, right? We're kind of dropping the softmax part. So if you will, this is called the linear attention model. It's actually quite used heavily today for computational purposes. So it's common to kind of use a few layers of linear attention models followed by a self-attention model for computational purposes. So it's, I think, a reasonable model here. And so in particular, we're going to use like a particular form for these weight matrices. Because we only care about extracting that final question mark, you can actually set this final weights in a very particular way. So that's kind of our architecture. You can think of it as a one-hidden, linear attention model, if you will. So very simple architecture. And for the data model, we're going to focus on kind of a linear regression kind of data. So what do I mean by that? So during pre-training, we are going to assume that demonstrations come from a linear model, right? So, but because, remember we had different tasks, kind of different classes of demonstrations, what changes between them, so the input-output pairs come from a linear model. What changes across tasks is kind of like the prior distribution of this linear coefficients. So, and this is according to a Gaussian model, okay? So for each task, we have a different coefficients, right? So different lines generating the data, but then we again see demonstrations of the form we talked about. Now at test time, you get a new task, right? So generated with a new coefficient, right? So again, you see demonstrations, as in like the ARC challenge, but then now the coefficients are different, right? And so the question is like, does test time training, can you actually adapt to this new task, right? And so in context learning, there has been a lot of studies, including for this model. I know Denny and Taiji have interesting work on even single index models for in context learning, right? So a lot of interesting stuff here. But now, our focus was, what are the improvements you get with test time training, right? And so that is what we want to focus on. So just to put it in the format that we're interested in, so remember our demonstrations, let's say, are of size n. We get k new demonstrations at test time. How we actually do the fine-tuning in this setup is we're going to add these k new demonstrations at the end of the demonstrations that we already have. And this way, we can actually create k new fake data, right, to do the fine-tuning on, right? But in reality, we only have k new demonstrations, right? So that is just to clarify what I mean by these k demonstrations in this case is this. So that is our data model at test time, right? So we use this interleaving strategy to actually create these kind of fake data that we fine-tune on. And again, the fine-tuning is simple. You pass it through this linear attention model. You just update your parameters with a single gradient step, right? So here is our results for this. So this is for isotropic covariances where the coefficients are isotropic. We also have it for more complicated correlated stuff, but I won't go through it in this talk. Okay. So by the way, if you have any questions about the setting or setup, maybe it's a good time to ask now. Go ahead.
The algorithm at test time?
Yeah, the algorithm at test time is, sorry, I have it here. So this new test data that you have, right? You just fine tune the model, the parameters of the model, right? And here, because in practice you don't do many gradient updates, we will focus on doing a single gradient update at test time, right? So you fine tune based on the test data, the fake ones you created, one single iteration. Okay, and so here's the result. So this is like before fine tuning. This is your loss, right? And this is your loss after fine tuning. So we want to see kind of how much did your loss go down. Okay, so in this case, actually understood again based on the literature that I talked about. It's well understood what is the loss in the setting if you don't do a test time update. It's something like this. So, and now if you compare it with this, you can see that basically you can actually kill this loss effectively by this difference, right? So in particular, if you have a few in-context demonstrations plus some test time samples, you get a significant drop in the loss, right? So again, think of like K being as order D, right? And N being small. So this is order 1, this is order 1, they cancel each other, right? And so you get a significant drop even after a single test time update. And in fact, this is something that you do see. This is with the toy model. I'll kind of show you results in a second with a semi-realistic model. So you can, this is the number of gradient steps you do at test time. You can see already most of the drop in the loss is actually after the first iteration. You get some improvement, not by much. So at this point, it's not computationally beneficial to really do more iterations. These curves are for different learning rates, just to show you that we're not doing anything funny with the learning rates, right? So that is the result. So yeah, basically a single step of test time training can capture a significant improvement already. This is kind of the right trade-off. You probably don't need to do many. Again, in practice, they didn't do that many iterations either. Like very few, in some cases, actually a single one. So this kind of explains some aspect of this. Another kind of aspect that I want to briefly mention is that you can also kind of read results, these results in a different way, which is you can kind of think of what test time training is doing equivalently as increasing the context length. What do I mean by that? Is you can kind of compare, you can kind of do the math and see that this is equivalent. The error you get is equivalent to the error you would get if you had a much larger context length, more demonstrations during training, pre-training, right? So in some sense, this may explain why you could have a smaller model that is much more capable once you do test time training, because as if you had a larger model with a bigger context window in some sense, and you can kind of mathematically figure out this transition. Of course, you can see this kind of like in our toy setup, but I'll show you in a second. You can also see these in a simplified kind of GPT model as well. We also kind of tried this for tabular data ourselves. So this idea of doing test time training, tabular data is actually a problem which transformers are not doing very well at. Like there's a lot of active research helping them kind of improve the models on kind of tabular data. But you can already see that even on this kind of tabular data, you get a significant improvement with test time training. And in fact, this increase in the context length that I talked about happens here. You can almost see sometimes a factor of 4 or 5, right? Even a single iteration of test time training improves performance of the models on tabular data. So that's one experiment. So maybe I should kind of mention this other thing, which is like there is also an interesting kind of transition point that you could study, because obviously at some point, if you have a lot of new test time data, you might as well not do pre-training, right? So you could study where that threshold is in this toy model, right? So this is kind of the crossover threshold where after this, you might as well not pre-train at all, right? You could just use only your test time data. It's kind of like, you can think of it, there's a distribution shift. You're better off, right, to, if you have enough samples, to just train on the fake test time data versus pre-training. And you can kind of characterize this in this toy model exactly using our theorems. And by the way, all of these curves are empiricals are dots. Solid lines are predictions. Clearly, they match. But you can also see this in semi-realistic. I mean, honestly, not really, because this is GPT-2. But you can kind of see similar phenomena happen in a little bit more realistic models as well, where you can clearly see there is a transition where this happens. But before I kind of wrap up this part, I do want to mention there is actually still some things that are a little bit not covered by this kind of simple theory. It's actually like related to the people, to the audience. So maybe you can help us. So if you see, our results, like this kind of threshold happens with k order d, meaning like the test time demonstrations you need is actually proportional to dimension. Whereas if you look at like the more practical setups, right, the number of test time demonstrations you need is actually significantly lower, right? So these are like multi-million, almost billion parameter models, some of the GPT-2 models, but you see like this threshold happens at 10, right? And personally, I think it should be kind of log, right? So that's at least what we hope, right? That with only a few test time demonstrations, you can get a significant improvement, right? And so on. I think this is, our theorems are correct, and I think they're sharp, but it's because I think we assume a linear model, right? So for those of you who have actually worked on nonlinear in context learning models, right? So I think potentially this is a good opportunity to show that in fact you need much fewer test time samples if you use a nonlinear model. So I think this is a product of us doing a linear model. So that's kind of one drawback of this result that I wanted to mention. Okay. So we have other results, including more general covariances and so on, but I don't want to talk too much about them. So let me actually end this part. Pause briefly to see if you had any questions about this first part before I go to a more classical setting. Go ahead.
Which parameter is updated? So
Sorry?
Which parameter over
the parameters of the model, the entire parameters of the network.
Entire parameter, QKB. Or
Yeah, exactly. Okay. So here, the last one we fixed because you just need the last question mark, the other two basically. Exactly. Other questions? Okay. So if not, I'll kind of like switch gears. This is not a single step analysis. This is kind of the entire trajectory. And here the focus is on simple neural networks. And honestly, it's kind of embarrassing that we're still stuck in this world of simple neural networks, but it is where we are. So this part is actually joint work with my student, Berk and Changzi, both at USC. So, and it's kind of like a surprising unresolved problem. Which, like this experiment you've all seen, right? I'll even tell you theory about it, even in a simpler setting. But basically, like if you have a planted model, right? So the data is generated according to a network with 3 hidden units. If you train a model of the same size, if you run gradient descent on it, I don't know if you know this, it doesn't work, right? So you actually hit a local optimum, right? But if you actually over-parameterize the model in the sense that you add more hidden units and then you run gradient descent, all of a sudden you do achieve global optimality. And for this exact setting, we still don't understand how this works, right? The one question is like, how do you get global convergence guarantees for gradient descent from random initialization? Of course, we can get to global optimality in these settings, but not ones that generalize particularly well. And so the real challenge, of course, is to find parameters that also generalize well. And kind of the issue here is that when you do over-parameterize, there's a lot of global optima in the training loss. And then the question is, which one do you converge to? In this setting, like if you kind of initialize somewhere, for example, small, you get one global optimum. if you initialize somewhere else, you kind of get a different global optimum. In terms of, training loss is always kind of 0, but they have significantly different test error, right? So really the question is like, we need a better understanding of the trajectory of gradient descent to figure out where, you actually converge to. Of course, in other settings like classification, a lot of people have worked on this, right? Like Matthews, for example, has a lot of nice results in this setting. So, but in this particular setting that I'm talking about, there's still a lot of challenges remaining. And so this is like, a lot of people have talked about this. This is also like at this kind of like forefront of this different regimes of lazy, non-lazy, feature learning, kernel learning regime, right? And I really like this visualization, which originally appeared in this paper by Lenka Shizawa and Francis Bach, which is like, so here, in order to kind of visualize the training of one hidden layer models, right? What you could do is you could visualize each of the hidden nodes as points in higher dimension, right? So here, I'm assuming the input is 2-dimensional, so I can just visualize it as 2D points. For each hidden node, I get a point, which is just the base coming into it. So here, I'm assuming the planted model has like 3 hidden nodes. So those are these 3 directions. And then I can visualize the hidden nodes as dots in this plot. So as we run gradient descent, you can then follow where these dots go, right? So if you are kind of in this non-lazy feature learning regime, if you will, what happens is very interesting. You start small, but all of them eventually align themselves with one of these 3 directions. Whereas in like the lazy or kernel regime, something I also worked on quite a bit a while ago, you actually kind of move around a little bit to hit global optimality, but you don't learn anything useful. You don't learn the underlying pattern in the data, right? And in some sense, this is why you don't generalize, right? So unfortunately, this setting we still don't really understand. Like with a planted neural network model, we still don't understand. In some sense, like our existing theory doesn't really apply. We don't really have theorems that really cover this plot yet. Of course, there is the mean field regime, but it still doesn't really capture this experiment fully. But I just want to say, even in a simpler setting, we don't understand. And this is the focus of this talk, actually, which is just a linear version of this problem, which is the target function is linear, right? So I'm actually just trying to learn a linear function. I fit a one hidden layer model to this, and again, we don't understand. And so it's again the same plot. You can see with small initialization, the model actually aligns itself with these 2 directions. When you go moderate and larger, you kind of get a mess, right? So even in this simple linear version of the problem, we don't understand this. Actually, you may be familiar with a lot of work, including work I was involved with, where you have polynomial target functions, but if you look at all of those literature, they explicitly exclude linear functions. So surprisingly, linear functions are quite tricky. And one way to kind of see, maybe appreciate the difficulty is that there's this interesting pairing behavior that happens in the linear case, which is like the nodes become exactly opposite of each other, right? So you can see as you run gradient descent, the final answer, there's 2 with exactly different signs. This perfect negative alignment happens. And so this is actually theoretically kind of challenging to analyze this behavior. So that is kind of, this kind of setting is our focus. Of course, it seems like a very toy setup, but I do want to mention that even this, also like historical context, for those of you that come from a compressed sensing background, we also observed this kind of problem, and we had difficulty solving this kind of problem in those days. For those of you coming from NYU, like my office mate, Carlos Fernandez Grando worked on this a lot. So yeah, like we would see these weird pairing behavior also in the super resolution problem. But this is a little bit of a tangent. If you're not coming from this community, you wouldn't care. So, but I do want to mention, even this simple toy setting covers somewhat fundamental problems. Linear targets, I think, are already kind of useful. In particular, think about denoising or autoencoders. This is kind of where you're trying to learn a linear map, right? So you're trying to denoise a signal. So you're kind of trying to go from X plus noise to X, right? So that's kind of learning identity. Autoencoders, the whole idea is that you want to regenerate X, right? So you can kind of think of this as a step toward understanding the training dynamics of a simple autoencoder, one hidden layer autoencoder. So that is kind of the motivation. And now, let me tell you the theoretical setup where we analyze this problem. So I like Gaussian data. So the data is going to be IID Gaussian. The target function, as I mentioned, is linear, which I just want to remind you can be written as the negative of 2 ReLUs. So you can think of it as one of the simplest cases where we're analyzing 2 ReLUs, right, instead of 1, which has been analyzed. So the model is a one hidden layer ReLU model. To make things simpler, I'm going to fix the outer weights. This is something that we can actually somewhat handle now. But we're going to fix the outer weights. We're just going to train the inner weights for now. So the population loss is like this. If you actually take expectations over the Gaussian, and we have both results for the population and empirical. And here you would run just gradient descent on the weights and try to analyze this. I do want to mention that this landscape here is actually quite tricky, right? In particular, is not benign in the sense that it's not a strict saddle landscape, if you will. So it's no guarantee that gradient descent works. So here is one initialization, for example, where you see it actually gets stuck in a non-global optimum, right? And in fact, this is not just like a kind of like a weird example that we constructed. So if you actually initialize weights here randomly around this point at any of these given radius, you can see that it doesn't work. This is the probability that it doesn't work. It doesn't, right? So you actually do not converge to the global optimum. So the landscape is fairly non-trivial, okay? And I'll tell you exactly in a second what the landscape is. But you can see it's only when it's much, much larger, right, that it starts to work, right? So in a good part of this region, things actually don't work, right? So gradient descent doesn't work. So that's why it's kind of tricky to analyze. So let me first characterize the landscape in a population case. So we can actually do that. So it turns out that the only global optimum here is actually the right answer, A and minus A. But it turns out that there are a bunch of non-strict saddles in this case. So these are where they are. And by non-strict saddle, I mean that gradient is 0, but the Hessian is also 0. So these are not, you cannot use somehow the saddle escaping theorems or techniques to escape from them. But nevertheless, gradient descent just works, right? And so that is the mystery you want to resolve. So the landscape is not good, but somehow gradient descent, at least from random initialization or small initialization, actually works. And so that's what we want to do. And so this is just a pictorial characterization of landscape. This is the gradient in kind of this a subspace spanned by the A directions in both W1 and W2. And you can see like gradient is actually 0 all of these places. The global optimum and a bunch of non-strict saddles. And here's like the actual loss. You can see why you could get stuck here, right? Even in this two-dimensional cross section. So you have the global optimum here, but you have kind of like stationary points that are suboptimal that you can get stuck in, right? They're not local optimum, but they're not saddles that you can easily escape from. So that is the loss landscape. But again, gradient descent kind of works. And so here's our theorem showing that gradient descent actually does work. So here's a result. You use a constant step size. If you initialize, so this is purely deterministic result now. When we go to the empirical, we can't prove as strong of a result. But if you just initialize small enough, right, in the sense that the sum of the weights are smaller than the target function by half, honestly, you can make this constant arbitrarily close to 1. That's not too important. Then if you run gradient descent, you actually get a fast geometric convergence to the global optimum. In this case, remember that the global optimum is the first weight is A, the second one is minus A, right? So even though the landscape looked a little bit ugly, you run gradient descent, you converge to global optimum, right? This is the population case. What happens in the empirical case? Unfortunately, I actually tried very hard. I could not prove as strong of a result. So in the empirical case, for technical reasons, we actually do need random initialization. So now we run gradient descent from random initialization. We're again doing this funny thing of using 2 different step sizes, although both of them are constant. I think a lot of you can guess where that comes from. But basically now, even though it's random initialization, but it just has to be, the standard deviation has to be small enough. And this is actually comparable with what we saw in the previous slide, right? So this is exactly the same size we saw. If you have Gaussian random vectors, this is the correct scaling. But we could not prove the deterministic version anymore, like not for any W1 and W2 for technical reasons. And this is kind of the right scaling. Like if you do a 1 hidden layer model, the standard scaling in PyTorch is of this order. So in some sense, it's completely in the practical regime of operation. Again, even in empirical case, as long as you have constant number of dimension samples, you do converge to global optimum. This is not the sampling fresh at every iteration. We're reusing samples. So this is really a legitimate setup. We have n samples at the beginning. We reuse them to run full batch gradient descent, right, on these n samples. You can repeat them. That's not a problem, right? So that is the result. So that's kind of the empirical version. You again get fast geometric convergence to global optimum. Again, W star here is like A n minus A. We still haven't fully figured out the overparameterized case, but let me maybe mention a result in higher dimension, which kind of corresponds to the autoencoder case, which is like, even if you have multiple outputs, right? So your target is not just a single A. It turns out most of the theory goes through. Here, again, we have to fix the output layer. So here we fix it as a V and minus V. If you were to run gradient descent on both layers, you would actually see this pattern, right? The second layer would be of the form a pairing of V and minus V. So that's why it's a legitimate setup to look at. But we're fixing this second layer, and we're running gradient descent again on the inner weights. So it turns out that the empirical result more or less goes through. Nothing is really changed. Again, we have to kind of initialize at random, sufficiently small. Then gradient descent converges at a geometric rate. Of course, here you need more samples because you have k outputs. So you need k times d number of samples. But then gradient descent works. Again, think of the simplest setting, which is just an autoencoder. You want to learn identity. Then you can set V equal to identity, and you get the result. Here, what is W star, though? A little bit different is like V transpose inverse times A and minus V transpose inverse times A. Again, if you were to run gradient descent on both layers, this is exactly what it would converge to. So it's a natural setting to look at. So yeah, that's kind of the results. Maybe I'll pause to see if you have any questions about the general form of the results. If not, I'll kind of tell you a little bit about how the proof works in this case. Questions, comments? Go ahead.
So if we have the label noise, and we need to take the smaller initialization, or we need the more sample complexities?
So if you have label noise,
yes.
So I don't think you need more sample.
Okay, go ahead.
I don't think you need more sample complexity, honestly.
Yeah.
But sample complexity may help you improve the denoising that you get.
Yeah.
But I mean, we haven't analyzed noise, to be honest. But typically the way these results would work is that you do a perturbation analysis to deal with noise, and then the final noise that shows up in your final answer will decrease with the amount of samples you have, effectively. Yeah. And so I think basically, you need more samples to do more denoising, but the base sample complexity should be the same.
I see.
Yeah.
So do we need a smaller initialization?
But in practice here,
Yeah.
You need small, but you don't need random, I think, in this model, right? But you do need small. I think if you don't do sufficiently small, you do get stuck in those bad regions. So I think you do need the small part. But what I was saying is, like, I don't think you need the randomness part. I'll maybe get to it when we go to the proofs. There are technical reasons where the empirical result is not strong enough to handle non-random, initialization.
I see. Thanks.
Go ahead, Denny.
So my intuition is that if you initialize sort of small enough, there's a radius where if you initialize within this radius, you will converge globally.
Yeah.
So the converse is not true, right? So is it the case that if you initialize outside, you will always get stuck at this?
Oh, no, yeah, that is also not true. But so we haven't really characterized that well enough. So we are kind of in the opposite direction. But I also don't think it's a trivial thing. So there is actually definitely a non-zero probability, right? So if you were to uniformly sample from that region, for sure, there is a constant probability that you can get stuck, at least a constant. But yeah, we don't have that everywhere it would not work. Yeah. I assume it's only in a part of that region. Good question. Other questions? Okay, so maybe I'll tell you a little bit about the proof until you tell me when you have to finish. Let me start with the population. Actually, the population and empirical kind of have different proofs. As you can imagine, the population, though, I think in some sense is more interesting because it's kind of deterministic. So remember, our goal is to show that the distance to the global optima decreases. And I really like this recipe. I kind of used it almost a decade ago in a paper on phase retrieval. So obviously I had to try it here, right? And so the recipe is very simple, which is like what we called back then local regularity. I guess the correct terminology for it is like pseudo convexity or something, which is you try to show that the distance to the global optimum, the correlation of the gradient is sufficiently large, right? This, you can think of it as some sort of strong convexity, but in only one direction, the direction to the global optimum. And then, some form of smoothness, right, typically. This is if you have this, you of course get fast geometric rate of convergence. Neither of these two are true though, right? Because remember there are saddles. So by definition, there are points where the gradient is 0, but you're not the global optimum. So this can't be true. And of course, this is also not smooth. In fact, if this ratio grows large, the function is actually not smooth. So this is just because even though you're averaging the ReLU, it has a well-defined first derivative, but the second derivative can go out of control, right? So neither of these is true. So in some sense, it seems like this classical recipe is not applicable. We actually spent a year trying other techniques because of this, but somehow we ended up coming back to this. And how did we come back to this is that, even though this classical recipe doesn't seem to be true, somehow these inequalities do seem to be true on the trajectory, right? If you start small, you run a gradient descent. On the trajectory of gradient descent, this stuff seems to hold, and you are getting, both the losses going down, the distance to the global optimum clearly going down, right? So it seems like maybe this classical recipe after all is not so bad, right? Things kind of seem to be monotonically decreasing, right? So that's why we kind of try to show these inequalities just on the trajectory, the first one at least. The second one, we kind of simplify a little bit. We just show gradient is bounded. So this is kind of a one-directional. Even though smoothness doesn't hold, this kind of smoothness to the direction of the global optimum, right? But we can only show this, remember, on the trajectory if you are initialized in this neighborhood, because there are non-strict saddles. Otherwise, this cannot be true. So, and how do we show this? We need somehow a control of the trajectory, right? We need to have some defining characterization of this trajectory. It turns out, you can think of it the way I like to think about it. You can define an auxiliary Lyapunov function, an auxiliary thing that goes down that controls the trajectory for you. In this case, the thing that we discovered is that when you run gradient descent, this sum actually is always monotonically going down. This allows you to control the trajectory. And so then you can prove these conclusions on this trajectory. So that was our observation, that this quantity goes down. It turns out to be pretty simple in this case. In other cases, including the multi-dimensional case, it's not so simple, actually. So basically, if you have a step size less than a constant, this auxiliary Lyapunov function goes down. And so because of this, you have some notional control of the trajectory, and then you could try to prove these inequalities, right? And so this is exactly what we did. But by having this control, then we could prove those inequalities on the trajectory. And you can see that these quantities indeed go down. And notice that all saddles that we talked about, this quantity is actually high, right? So by controlling this, we actually make sure that we never go to the bad region. Okay, so we do avoid the saddles. And so for local regularity, there's also some clever trick that we played here. Actually, this is one of the only instances that GPT was somewhat helpful. But basically, it's like, we are trying to lower bound this quantity, assuming this holds. What you could do is you're trying to show this for all, W1, W2 that obey this inequality and all A. So if you want this inequality to be true, it better be true for the minimum A. And then after you minimize this is a quadratic in A, so you can actually close form minimize this. The final thing only depends on the angle between W1 and 2 and the ratio. If you want to show an inequality in 2D, what do? You just draw it, right? So that's what we did. So then you can easily visualize it, and you can also turn it into a formal proof, but at that point it's not really needed. So same trick, so it's positive everywhere. So on this trajectory, you can show this correlation holds. Similarly for smoothness, you can follow a similar recipe. Here you're maximizing over A instead. Again, because it's a quadratic function in A, and then you can also show this inequality in a simple way. So that is like the kind of trick in the population. And the rest is classical, right? Because if you assume those regularity conditions, you just plug it into the update formula, and everything works out. I'm sure a lot of you have seen this, so no need to annoy you with this proof. So what about the empirical case? So this is where things get tricky. The empirical case, we're kind of relying more on a local analysis. So this is where this kind of first iteration analysis becomes powerful. In this case, what we can show is that the first iteration of gradient descent kind of gets somewhat close to the right answer. And then we try to show the result locally. But this is where the randomness is actually quite important at initialization, both randomness and smallness, because if you don't have both, we could not show this. But I honestly don't think this is needed. I think deterministically this result is still true, that you converge globally if you have the sum. But basically, if the sum of W1 and W2 are small, it's just like the empirical concentration results are not strong enough to handle that case, unfortunately, yet. But that's kind of the first step. So you show the first iteration is close. And then, again, this proof is based on like the spectral bias of the first iteration. I did this thing with ReLUs, like in 2017, there's quite a few. We were talking over lunch. There's like this Stein lemma ideas, this isotonic regression ideas that basically apply here also. So I won't actually go through that analysis. This is kind of the analysis for a simple ReLU kind of structure where you can show the first iteration kind of picks up a good bias. The real challenge here is really the subsequent steps. I will not talk too much about that, but basically here the idea is that you have to show this kind of regularity condition locally. The smoothness is honestly fairly easy to show. But here the tricky part is we're not reusing samples, right? So you use the same samples in all iterations. So you kind of have to show, so W depends on the samples itself, right? So you need very refined concentration and empirical process theory here to actually show this, because this is a random quantity. W itself is also random, and they depend on each other in a very complicated way. So you have to show this kind of uniform concentration of this around the population. For the population, you know this identity is true. So you have to show a very good uniform concentration here. This honestly is probably the most interesting part of the empirical analysis, but I will not get into it because it's very technical. But if you're into empirical process theory, it's kind of a nice argument, I think. So if you want to take a look at it, but that is the trick there. And this one honestly is not that hard. So here you can also use empirical processes, but a much less fancy kind. So that's kind of the idea. But as I said, the arguments here are quite technical because we're not using fresh samples, and there's a lot of Gaussian comparisons and Lagrange stuff coming up basically. So so I didn't actually talk. I forgot to talk about the multi-output case. That also requires a little bit of extra steps there, but let me actually kind of wrap up here. So just to conclude, like I talked about two different things. So the first part was like, how can we start to analyze this kind of test time compute ideas, but in a very simple setting? I would say our simple setting was like, essentially was how does test time training help address kind of distribution shift in an in-context learning setup, right? Some very preliminary theory. I'm quite excited about this area. I think there's much more to be done. And speakers today already talked about that a little bit. I think much more to do here. And then the second work, even though it's a very classical problem, I'm kind of excited about it because it's about really analyzing the full trajectory of gradient descent. And what we showed is that the gradient descent trajectory can indeed escape even bad stationary points that are not strict saddle. And I think there's also quite a bit more to do in this space, right? Because we do know that even these one hidden layer models, the landscape could get quite complicated, but somehow on the trajectory of gradient descent, things are fine. And I'm hoping that this is maybe a good starting point to do those kind of analysis as well. And yeah, with that, I'll end here. Very perfect.
So do you have any questions and comments? Just to clarify, so in the second part, so as long as the initialization satisfies W1 plus W2 has a smaller norm, it converges. So even though W1 and W2 have a very large norms, but if they are canceling
exactly. Yeah, that's the result.
I see.
Yeah, so individually there's no constraint.
Oh, I see.
And in the population case, completely deterministic.
Then it will converge to the global field. I see. Other questions?
Go ahead.
For the multi-output case, you have to do some sort of matching with like the correct directions.
Yeah, exactly. So this is why I put the V and minus V. I actually don't know how to prove that when you do simultaneously, but it happens empirically. I actually can tell you even the V and minus V it converges to, but I cannot actually prove that it converges to there. So, but in this analysis, we don't even need to assume that particular V. We just assume the pairing of V and minus V. We fix V. It could be anything. We do gradient descent on W1 and W2.
And one other, or I have two small questions. The other is, you said GPT helped with one part of the proof?
Yeah.
Which was the part?
Like not really, but it was helpful in the sense of like, when we were kind of struggling to simplify this equation, it did suggest optimize over A, which is something that I had not thought about doing in this case. Even though it's simple, right, it's quadratic, it's natural to do it, but our headspace was not in there, and indeed when we optimized over A, because it's simple quadratic, then things simplified.
And I just have one other small question. It's about the first part of the talk where you did the test time inference. I just wanted to make sure I understood the gap from prior work. So there's a lot of prior work on the in-context learning, but my understanding is that all the prior works, they just prove that there exists a set of weights for the transformer such that it performs. So yours did the test time inference to find the weights.
So there's also a result that says like on the pre-training data, if you run gradient descent, I think there's even a result that says that works, right? I forget by who that is. And definitely the Taiji and Denny have a result, I think, even in a nonlinear setting. I think you mentioned that even today, right? But yeah, so this additional, what is the effect of test time training was not there.
Mahdi, I want to ask a relatively general question. So in your test talk, you say that, okay, for this non-convex problem, it can be solved by gradient descent. Okay. So my question is, normally previously people do prove some form of hardness of gradient descent. So now I want to ask you this question is, what kinds of the loss landscape is easy for gradient descent? I think maybe this is an open or quite general question. I would like to hear your thoughts about this.
So honestly, I don't know about the landscape, but in these planted models, I can tell you what kind of neural networks I think are easy to learn.
Yeah.
And it actually ironically goes back to the compressed sensing days. So I think as long as the weights, the inner weights are sufficiently separated, I think that's an easy learning problem. But somehow, and I know that even with Gaussian marginals, there's a lot of results that tell you cannot learn one hidden layer models, right? You know, Adam Klivans and his co-authors have an interesting paper on that. Even with over-parameterization, we can learn it. But this is all for worst-case weight patterns. I think basically, as long as the weights do not cancel each other with a negative direction, so this is kind of an incoherent assumption in some sense, then I think the landscape, gradient descent works for sure. I don't know what landscape allows you to do that, but gradient descent does seem to work, and so that is the underlying challenge I really would like to address, actually.
In your today's talk, so how can we to describe such loss landscape?
Yeah.
So
here, they're exactly the negative of each other with a negative sign. So I think this is a benign planted model. So, but imagine if you have kind of correlated directions, but negative outer sign like here, then you would be in trouble, right? Because they almost cancel each other to make it zero.
True.
So that is why I think this is kind of benign, because again, this kind of incoherence is there. Like they're kind of pi angle away from each other, right? So they're kind of not on top of each other.
Thanks.
Yeah.
Okay, so I'm interested in the second part of the proof techniques. So you just use a Lyapunov function constructed by W1 plus W2, and it's relevant to the Taiji's question, I guess. So how can we widely apply the similar techniques? Because I guess the structure here is just like the second layer only has a +1, -1, so that result in that symmetric form. So how do you expect to?
Yeah, honestly, we even found this one by accident, because actually proving this is, okay, if you write it down here, you just have to show something about the sum of the gradients, because it's just W1 plus W2. So it ends up being there is just the right cancellation that makes this go down. But in general, I think this is the part that is not so easily generalizable. Even in the multi-output case, we had to become creative. So there, I honestly do not have a good recipe for that. So that is, I think, where there is a little bit of art involved. What goes down is tricky. But what I can tell you, there's actually this interesting theorem in nonlinear dynamics that tells you if you have convergence, such a Lyapunov function always exists. There's kind of this maximum Lyapunov function theorem. So they always exist, but how do you find them is kind of an art in some sense.
I see. For instance, that's the one you show to us is just the totally symmetric case. But for instance, how about like adding a very small perturbations, and can we still have approximately the convergence, or did you?
Oh yeah. So that still works. Are you saying like if they're not exactly negative of each other?
Yeah, for instance, so in the today's case, so you just show the second layer is totally +1 or -1, so it's totally symmetric. But for instance, we have very small perturbation to the second layer.
That is actually fine, because you can actually do a change of variable, incorporate that change in the inner layer. Because you imagine you have 1 and 2, 1 and -2, you could give the 2 to the inner layer, and still pretend it's 1 and minus 1.
Okay.
So that is not the big issue here, I think.
Sounds good.
Yeah.
Thank you.
Okay, so we have already run out of time. So let's thank the speaker again.
Thank you.
Thanks a lot for organizing this workshop, Taiji, and it's great to be back in Tokyo. So I'll talk about some of our recent works on learning shallow two-layer neural networks. These will be, there's going to be about 50% overlap with Murat's talk earlier today, so I guess I won't need to go over a lot of the definitions. But what I would want to emphasize is that there will be some findings, like the high-level message are similar, but then the proof strategy is totally different. In fact, the strategies that I'm presenting today cannot handle this quadratic setting that Murat presented earlier. Okay. So I'll talk about two papers. One with Taiji and his former students here at University of Tokyo, and Riken AIP, Kazusato and Eugene, and the other with Jason at Princeton and his students Ishan and Yunwei. Okay. So I will first introduce this problem class of Gaussian single index models. So where my input is d-dimensional isotropic Gaussian, and my target function only looks at one direction of the data. So I'm projecting this isotropic Gaussian in this direction's data, and on top of that, I have a nonlinear. You can think of it as an activation function. It's also referred to as a link function. So we will assume that this link function is a polynomial with degree p and information exponent k, which I'll introduce in the next slide. So the rough intuition is that this is to learn this model efficiently, you need a procedure that's, because this target function only depends on one input direction. Right? So you need some kind of adaptivity to this low-dimensional structure. So we know that this model have basically d parameters to be estimated, right? Because this theta is a d-dimensional vector. So information theoretically, n equals d sample should be sufficient to estimate this target function. But then it's possible that in order to achieve this optimality, you need exponential compute. Right? So if we restrict ourselves to algorithms with bounded, say, polynomial compute, then it turns out that often we cannot achieve this linear and d sample complexity. So for example, if we restrict ourselves to just kernel methods, then it is well known that despite your target function only depends on one direction in the input, kernels will have to pay d to the degree samples, so d to the p samples, to learn this, to achieve low loss when sigma star is a degree p polynomial. So this is a pretty big gap, right? And this lower bound also applies to neural network in the lazy or kernel NTK regime. There's been a lot of prior works that try to study the complexity of some sort of adaptive algorithm. So let's say instead of fixing my features at, say, random initialization, if I'm allowed to train the features, say like if I'm training a neural network, I'm training both layers, then what will be the statistical and the computational complexity? So it turns out that for a large class of gradient-based training algorithm, the complexity is determined by this notion of information exponent. For that, I'll need to introduce a Hermite expansion of the target function. So this link function sigma star, I can decompose it into the Hermite bases. So HE, these are the Hermite polynomials, and so the Hermite coefficients alpha j, these are defined as basically how much you correlate with the j's Hermite polynomial. Okay, and the information exponent is defined to be the smallest integer, such that the some small integer k, such that alpha k is non-zero. Okay, so it's sort of, this is the lowest degree in your Hermite expansion. Okay, and by definition, this is always smaller or equal to the degree of the target function, right? Because the degree is like the highest term in your expansion, and this is the lowest term. Okay, and this it's not entirely clear why this term relates to the hardness of learning for gradient-based methods, but the rough intuition is that for a particular kind of gradient-based update, this captures how much information you have in the gradient around initialization. So the way to see this, I guess I'll just quickly sketch the intuition, is that if you look at the population, the gradient of the population squared loss, which I will approximate with the correlation loss, because if I assume the output of the model is small, then because of the Gaussian input, I can Stein's lemma this correlation term. And then by Stein's lemma, I actually get the direction theta. And this is what I want, right? Because we want to recover the direction of the target function. And then there's going to be a scalar term that tells me how big the population gradient is. And the scalar term is essentially it's the inner product between the two single index models, and where the direction is pointing at theta, the target function, and w, my student weights. Okay, and just by properties of the Hermite polynomials, I can expand this expectation as a sum over inner products raised to the j's power. Okay, and the main observation is that in high dimensions, so w, so this is think of this as my initial neural network weights. This is going to be almost orthogonal to the true parameter. Right? In fact, this overlap is going to be of order 1 over square root of d. So what this means is that in this sum, the higher order terms, because they're raised to a higher power, they're going to be smaller. Okay, so meaning that this sum, at least around random initialization, is going to be dominated by the lowest non-zero term. Okay, that's going to have much larger magnitude than all the remaining terms. And this is what the information tells you. Information exponent tells you. It tells you what is the degree of the index of this lowest term. So the intuition is that if the information exponent is large, then this gradient is small because you're raising this vanishing inner product to a higher power. Therefore, you need more sample to concentrate the gradient, right? And that implies a larger sample complexity. There's been at least probably 20 papers in the past 2 years or so that show that if you run a gradient descent, squared loss, or correlation loss on a two-layer neural network, you're going to learn this is sufficient sample complexity of something like d to the theta k. I'm hiding this exact exponent. It could be k minus 1 or like k divided by 2. But the point is this k shows up in the exponent in place of, in contrast to the degree p, as in the kernel of lower bounds. Okay. So this means that neural network can, if you train it with gradient descent, it usually does better than kernel. Right? Because for kernel you pay d to the p, and the degree is always less than the degree is always greater or equal to the information exponent k. Okay, and so this is an upper bound, and it turns out that there's also a way to relate this information exponent to some sort of computational lower bound. So for that, we need to talk about the statistical query model. So the rough idea is that to characterize the computational or statistical hardness for learning the single index model, we can sort of count. So if I look at the gradient of the squared loss, you can see that the information of the target function comes from the label y, right? And so the information, well, if we restrict ourselves to the squared loss, come from a correlational query. So essentially, I'm allowed to choose my function here. This is this is like my gradient of my neural network. But the query, the information that I can query is the correlation between this sort of function and my labels. So this is referred to as a correlational query. So to characterize the computational hardness, we can count how many accurate correlation query you need to make in order to achieve a small loss for estimating this target function. So basically, there's two different kinds of query here. One is we look at the first, we can start with the most general, like full statistical query model, where you can define functions that are that depends on both x and y, your input data, and the labels. And there's a correlational restriction, which tells you that you're not allowed to change y. We can construct this function, which is like the gradient of my neural network. But then I can only query this correlational function. And the way we connect this to, so for the statistical query lower bound, there's going to be two components. One is we will count how many query we need to make to And the second is that, remember, we should think of this as a population gradient, right? Because it's expectation. So to connect this to a sample or a statistical guarantee or a statistical lower bound, we will introduce some tolerance tau. Okay? So this heuristically, you can think of this as representing concentration error. So think of this as a population gradient from a correlation term, and this Q tilde, this is what I actually have access to. This will be like some perturbation of the population gradient, and you can set the perturbation magnitude to be 1 over square root of n. So it represents concentration, the concentration error. So this is a heuristic because in the actual SQ model, this tau, this could be worst case noise. This is not necessarily the concentration noise. But if you buy this heuristic, then there's a lower bound that tells you that if you want to learn a single index model with information exponent k, if you restrict yourself to correlational queries, then you need something that's exponential in the information exponent. So this quantity does indeed show up. But whereas interestingly, if you don't restrict yourself to the correlational query, if you have full SQ, then you only need linear in D many samples. So this is telling you that essentially this information exponent kind of entails some upper bound on sample complexity and compute for gradient-based learning of two-layer neural network, and there's also some corresponding statistical query lower bounds for this. Are there any questions? So these are some of the prior results. Yes.
Can you remind me what are the best upper bounds known for
learning
gradient descent?
Okay, it depends on what kind of query, what kind of loss you use, right? So if you restrict yourself to correlation loss and you do online SGD, then the best rate you get is d to the k divided by 2. But if you're allowed to change the loss or reuse data in a specific way, then basically you're implementing not a correlational query, but a full SQ. So then you get something like d polylog d. So if the f star is a polynomial. If f star is not a polynomial, then there's an analogous definition of generative exponent. Right? This is by Alex and Joanne and Jason. So basically it's saying that you can pick the best transformation of y. And so you pick your favorite transformation that lowers the information exponent as much as possible. Then the best algorithm is going to pay d to the k divided by 2, where k is its new index.
But gradient descent could potentially get to e.
Right. If you yes and no. So yes, in the sense that if you allow enough cheating, so if you're fine with modifying the loss or modifying, for example, if you allow yourself to see one new example in every 2 steps, something like that, then yes, you could get something that's close to this SQ limit. But for just vanilla training, say just doing ERM for full batch, I don't think there's any evidence for or against this. Okay, so this is sort of a class of functions that has been extensively studied, and for this work, we will be looking at a sum of a bunch of single index model, which has a name of 2-layer or 1 hidden layer neural network. I can define a 1 hidden layer neural network as basically a sum of a bunch of single index models. So I'm going to ignore the bias term. You can absorb the bias into the nonlinearity if you allow each of the neurons to have a different nonlinearity. And also, they'll be weighted by some second layer coefficient, AM. And we will make 2 very important simplifications here. One is that we will assume this the true coefficients, basically the index features are orthonormal. So we cannot cover the setting that Mahdi just mentioned, where you have 2 ReLU neurons pointing in opposite directions. So this is, if we remove this assumption, well, we can relax it to near orthogonality, but we cannot handle neurons that are too correlated. And 2 is I will make some assumption on this link function. For now, so the link function will be a degree p polynomial. This degree p part is not important, but this information exponent k, we will take k to be greater than 2. So we can only handle higher information exponent settings. I'll tell you why this is the case. So we make rather strong assumptions. This is not going to cover common activations like ReLU, but I guess to partially justify this, one reason is that it's because we want to look at this extensive width regime. So most of the 99% of the prior results on learning multi-index model considers the width of the teacher model to be very narrow, meaning that it stays fixed as you let the dimension go to infinity. Okay, so think of it. So this means that you're optimizing for like a tiny neural network. So the number of neurons is much smaller than the input dimensionality. Whereas here we want to go for the setting where as the number of input features gets larger, the width also gets larger. Okay. Of course, because of the orthogonality constraint, this alpha, this exponent in the width cannot exceed 1. Okay, so this is not necessarily a large width regime because ultimately the width of the network is still less than the number of features you have in the input, but this is already this is a much larger width than most of the previous works. And it turns out that this is where most of the technical challenges are at. Because intuitively speaking, the way most of the previous analysis work is that if you're trying to learn a finite width neural network, then you only have to keep track of finitely many what's called summary statistics. Basically, you track overlap with individual neurons, and there are finitely many overlaps to track. And you can probably write down some sort of ODE for these. But now, because M star diverges, you have infinitely many summary statistics. So even if you summarize the training dynamics in some like ODE, this is still going to be infinite dimensional. Okay. So just to motivate the setting a bit, the first, of course, is we want to learn a 2-layer neural network that's not too narrow. And I guess I'll skip this. There's also there's been a recent trend of using this shallow neural network as like a toy model for a mechanistic interpretability, where you can think about one neuron as like one skill that you pick up during training. And but this is not very important. Okay. So there are 2 questions that we ask. One is, does gradient descent work here? Okay. And 2 is, how hard is this function class? Right? This is a sum of single index models. So you would imagine probably the complexity is going to look like the number of single index model times the complexity required to learn one single index model. So we will establish this in the SQ sense. Okay. And so how does a student model work? So we will use the student model that looks almost like the teacher. This is also a 2-layer neural network with matching activation function. But for the first half of the talk, I will be cheating a bit in the sense that I will assume layer-wise training. Okay, so I have 2 layers parameter, the first layer W and the second layer A. I will not be training them jointly. I'm going to train the first layer first. Okay, so for the first layer, I will run gradient descent on the MSE loss. And because I'm assuming small initialization, this is kind of the correlation loss. Okay, so yes?
What's the order of the small iteration? I remember not so small.
First or the second. The first layer is just going to be on sphere because this is going to be a spherical gradient. Yeah. But second layer, I think we need something like inverse poly D. So
1 over D, okay.
Yeah, 1 over like D to something. Yes, yes. So I guess the side remark is that, so this is kind of like a mean field parameterization, but even though I'm writing it in the NTK way, I have a 1 over square prefactor. But here actually, because we're never taking the width to be that large, we're never looking at like a vastly over parameterized network. So it turns out that the scaling with respect to the width, like whether it's 1 over n, it doesn't really matter. It's about the scaling with respect to the input dimension. Yeah, so the idea is that we're going to first train the first layer, and the hope is that they're going to find all the teacher neurons. And after that, so that's the width of the teacher network. Yes, sorry. Yes, so this is the target function I'm learning with M star. And now I am trying to learn this network with a student network that's with N. And N will be something that depends on M star.
Okay, but so then your initialization will, okay, so N depends on M star. So you were saying that you need 1 over poly D
right.
Initialization, but then that is sort of mean field because it's scaling with 1 over M star.
Oh, yes, that's actually true, yes. It's just that, yes, we can actually keep, as M star grow, yes, that's right, because it also grows with D, so it's actually hard to like distinguish the two. Yeah, so this is, yes. Right, so it's actually hard to distinguish between these two quantities. That's right. Okay. And the intuition is really that the first layer, when you train the first layer weights, that's going to find you the direction. That's going to be the most difficult part, right? And after that, you will just train the second layer, which is a convex problem, because you use the squared laws to adjust adjust for the varying second layer magnitude. Right? This AM. Okay, so that's the training algorithm. And I'll tell you what the result looked like, and then what's not good about this. We will assume the information exponent is greater than 2. So this does not cover the setting that presented earlier today. For some technical reason, we cannot actually take alpha to 1. So remember alpha. So the teacher width is d to the alpha. So assuming the teacher weights are orthogonal, alpha should be something between 0 and 1. We can only do 1/2. So if you follow this layer-wise training paradigm, you train the first layer, and then you train the second layer, then this is how many samples you need. It roughly scales as m star, the number of teacher neurons, times d to the k minus 1. Okay, and because we do online SUD, this is also how many gradient steps you need. So this is a computational and statistical sort of upper bound. And this is the number of neurons for the student model you need. So it depends on m, but in some ugly way. So n is m star to the power of kappa. And kappa is, we refer to this as a condition number because it's kind of telling me how much the second layer weights in the teacher model can vary. Right? So these are the second layer, the teacher second layer weights. What the intuition here is that if one of the teacher neuron have huge second layer weights, then all the student neuron will converge there. So then you'll be missing out on the smaller ones. So we have exponential dependence. I'll explain where this comes from in a bit. But for now, let's just imagine that this kappa is like theta 1. So all the teacher neurons have roughly the same magnitude. Then everything is polynomial. Okay. And how does this compare to prior results? So if the target function is a degree k polynomial, then a degree p polynomial, then kernel ridge regression, or NTK, is going to give you d to the p, which is worse than the sample complexity. The more interesting baseline is this gradient-based training on multi-index models studied in prior works. So there's been a line of work that, so this target function, this two-layer neural network, is a subclass of multi-index model. Right? It's multi-index model with the additional assumption that the link function is ridge separable. So if you have an algorithm that works for generic multi-index model, it will work here. But the sample complexity for these prior works typically look like this. So there's going to be d to the k. This is sort of the amount of samples you need to find this low-dimensional subspace. Right? This is where the information exponent comes from. And then there's going to be another part that's m star to the p, because after you find this m star dimensional subspace, you have to sort of fit the link function. And so agnostically doing this, if you know the link function of the degree polynomial, is going to cost you m star to the p's power. This was fine in prior works, most of prior works, because m star is assumed to be constant. But now if m star is growing and the degree is potentially much larger than the information exponent, then this part could be dominating. Okay, and whereas here, we don't have any dependence on p. Okay. And the reason for this, this improved sample complexity is because of the fact that we take into account this rich separability of this link function. So most of the prior analysis on learning multi-index model is basically showing that after you train, so let's say my initial parameters are sort of isotropic, they're randomly initialized. After gradient descent training, well, which typically means one gradient step, you will find you're going to localize the parameters into the subspace spanned by the teacher, the target weights. Okay, so there's some sort of localization, and so you pay some samples to find this subspace, and on top of the subspace, you just do some sort of kernel regression. Okay, so this is where the second part, this m star to the p, come from. But now with this this additive assumption, what we can show is something that's much more specific. We can show that after you train the first layer weights, for each teacher model, or for each teacher neuron, there's going to be at least one pseudo neuron that converge to it, achieving strong recovery. So here I'm visualizing basically the horizontal and the vertical axes are two teacher neurons, and these colored dots, these represent the trajectory of the pseudoneuron. Okay, so you start here, but then after as online SGD training, at least for each other direction, you see some alignment. Okay, and this is why this, and after that, training the second layer is very efficient. Okay. Okay. So this is a sufficient sample complexity, and now for the SQ lower bound, so there are two different types of lower bound we prove. One is for the correlational query, where you're only allowed to access a target function through this correlational information, and then we have the full SQ. So for the upper bound, if you look at the sample complexity, this is kind of intuitive, right? Because the complexity for learning one single index model is like d to the k minus 1. And now you have m star in front of it because you're learning m star of them simultaneously. And this turns out to be also the CSQ lower bound here. So the CSQ lower bound for one single index model, if you recall, is d to the k divided by 2. Okay, and we have m star times that. Okay, so this is saying that at least for the correlational learner, learning one like big neural network with m star neuron is roughly the same as learning m star like a single index model like at the same time. Okay, so this makes sense. The part that does not make sense is the SQ lower bound, which is that so if you remember for the SQ learner, you only have to pay d samples to learn a single index model if the link function is polynomial. Okay, so I guess let me just go back. So here, for CSQ, we have d to the k divided by 2. But now for SQ, you only need d samples. So now if you follow this intuition, then this, it will appear that the SQ lower bound should be something like m star times d. You're learning m single index model in parallel, but that's actually not the case. Turns out that by varying the degree, but varying this link function, but while keeping it to be polynomial, we can actually this lower bound is going to be can be made arbitrarily large. So this rho can be for any fixed rho greater than 0. I can find some link function such that the SQ learner needs to pay this many samples. Of course, this is under this IID concentration heuristic. Okay. So from an SQ point of view, this function class is different. It does not. It's actually harder to learn than m star single index model independently. Okay. Okay, so for the interest of time, I will not go over how this result is proved, unless there's questions. Mm-hmm. Yes?
I just have a high-level question. Mm-hmm. How does orthogonality of the weights help with the gradient descent dynamic analysis? Because the W's are not, the inner weights are not orthogonal yet, right?
The students or the teacher?
Sorry, I confused the students.
The students, yes, they initialize random, yes.
Yeah.
Yes, so in about 4 slides, I'll get to that, yes. That's a very good point. Okay, so let me just quickly sum up. So for now, let's just assume we're in the well-conditioned regime. Let's assume this kappa, this difference in the discrepancy in the teacher second layer weights is a constant. Then these are what the complexity look like. So for kernel methods, learning anything degree p is going to give you d to the p. And if you do a one-pass SGD, you pay m star to k divided k minus 1, d to k minus 1. And this exponent is this is not optimal, but we get the same sort of a similar exponential dependence on the information exponent, whereas the SQ lower bound is quite different. So this information theoretic limit is something like m star times d. This is a total number parameter in your neural network. But even if you use full SQ type of algorithm, it's likely that you still need much more samples. So this suggests at least a statistical computational gap under the SQ class. So now, the thing that I want to revisit, especially in light of this, the second half of the talk, is what happens if the condition number become large. Okay, so the previous upper bound that I showed you requires the student width to be m star raised to this power kappa. So if kappa scales with dimension, then we're kind of screwed. Then we have to pay super polynomial compute. Okay, and so why do we care about, so I guess let me motivate this a bit before telling you why we get this exponential dependence. So why do we care about this large condition number setting? So for that, I guess I will be very fast because I think Murat gave this similar motivation. It's because we want to look at parallel second layer. Okay? We want to look at setting where AJ, the second layer weights of this teacher model, follows a parallel decay. And so for that, our starting point is that you have this neural scaling loss where a pre-training loss follows this smooth parallel and is a predictable type of curves. And on the other hand, you also have all these weird emergent capabilities, right? Where instead of, if you don't look at the overall pre-training loss, if you look at how well you perform on individual tasks, so say like modular arithmetic, then it's possible that you don't get the smooth parallel, but you get some sort of all or nothing type of sharp transition. So if you increase the compute, at some point, suddenly you pick up some, it's a skill. Okay. So you have smooth, predictable scaling and some unpredictable sort of emergence in the skill acquisition. Of course, whether this is real is still under debate, right? There's a lot of work arguing that it's because these two loss metrics are different, et cetera. But our starting point is really that in a neural network optimization, this sort of emergent scaling curve is very common, right? Basically, anytime when you start from a saddle point, then you will have an extensive plateau before the loss drop. So basically, there's a well-formulated hypothesis that tries to reconcile these two, which is the additive model hypothesis, which is saying that my cumulative, so for scaling law, I'm usually looking at the cumulative sort of pre-training type of loss. And the conjecture is that the cumulative objective can be decomposed into a lot of distinct skills. Okay? And each of the skills, learning each of the individual tasks can give you some sort of emergent scaling curves. But then because the loss is a sum of so many, and they have different sort of time of emergence, you get a parallel, right? So this is what it looks like visually. So let's say I'm learning one particular task and then the loss plateaus and then it drops. But then if I sum up over a lot of these drops at different time scale, I should get something smooth. Okay. So basically this the intuition is that the loss looks like this. Okay, this is an indicator function, so this gives you the emergence, but then you have a sum over a bunch of things with different weights, and this indicator function have a different time scale. Okay, does this make sense? Okay. And so now we'll study this two-layer neural network setting to try to sort of support this hypothesis a bit. So you can probably guess, so each of these curves will just correspond to how fast you're learning one teacher neuron, and then we'll be summing up all of these. Okay. So let's revisit the single index setting a bit. We know that the sample and the computational complexity of SGD learning often depends on the information exponent, which is the lowest degree in your Hermite expansion. But the more interesting thing, at least for this part of the talk, is that it's not just the sample complexity, but the actual training dynamics. So the phenomena is actually that if you plot the population loss, the generalization error versus time, you'll get something that looks like an emergent risk curve in the sense that there will be a very long time. So let's take k to be something greater than 2. There'll be a very long time where the loss doesn't drop at all. Okay, so you'll be around a saddle point and the loss plateaus. And this plateau is going to be something of poly D size. Okay. And then after a long plateau, the loss is going to drop to 0 in a very short period of time. Okay, so visually, what's happening is that most of the SGD steps is actually going to be spent around this equator where you're basically almost orthogonal to the target function. Okay, so the overlap with the true direction is something like 1 over square root of D. And you spend like d to the k time over here. The loss doesn't drop at all. And then once you escape the equator for a tiny bit, then you can ground wall, and then you get overlap in a very short period of time. Okay. So this is actually an example of emergent risk curve. And so now it becomes quite natural to look at this two-layer neural network. So because I'm looking at a sum of single index models, and we know that for single index model we have this type of emergent curves. So So there are two criteria, the two things that we need to keep in mind. One is that we want to look at high information exponent, so that there is an initial plateau. There is this extensive search phase where the loss doesn't drop. And then we want to vary the secondary coefficient so that the time scale where the length of the plateau is going to vary across different teacher neurons. So concretely, we'll still be looking at this extensive width setting. Okay. And now there's another motivation of looking at extensive width, which is that in order for this additive model hypothesis to work, because I'm summing a bunch of discrete things and I want to make it smooth, then basically I need to be summing over infinitely many of them. Right? So this is like this Riemann sum type of approximation. So the width cannot be small. Otherwise, I just get staircases. But now the condition number needs to be large, right? Because I need to take AM, the secondary weights, to follow a power law. So if the width m star depends on the input dimension, then if I set this power law, then now this condition number, this A max divided by A min, is also going to be scaling with the dimensionality. Okay. So now if the sample complexity scales with m to the kappa is the condition number, then this is super polynomial. Okay. So for the second half of the talk, we'll be looking at a slightly different, but arguably more natural training algorithm where we can actually show that this class of target function is learnable in polytime. And we'll have a very sharp characterization of how many samples or how much time you need to learn individual tasks. Okay, so let's revisit. So I think I'll answer Mahdi's question now. It's just that why do we place the assumption of high information exponent and orthogonal teacher neuron, and why does this analysis fail when the condition number is large? So just to recap, previously we look at layer-wise training. We train the first layer first, and then for the first layer we do this correlation approximation to the MSE loss, which means that the interaction between neurons are ignored. So each neuron will just be attracted to one of the teacher directions. The squared term is ignored, so the neurons don't really interact. And then after the first layer finds the right direction, I will train the second layer just to fine-tune the account for the magnitude. Yes.
Do you run the first layer for one iteration? Or
we need poly-D iterations.
Okay.
Yes. So this is actually quite crucial that the first step is because for the first step, unless you use a huge sample size, otherwise after the first step, you'll still be at the equator because the information exponent is high.
I was confused because sum of values is right in the middle, right?
Oh, right. So this can't handle ReLU because the information exponent is greater than 2. So we subtract the lower order Hermite modes.
Can you remind me the assumption of the student activation question?
They're always going to be well specified. So I'm going to use the exact same activation as the teacher.
Okay.
So yes. Okay. So how does this analysis work? For the theorem I introduced in the first half. Well, so if you look at the correlation, the correlation loss when the information exponent is high, what's going to happen is the following. So let's just zoom into one student neuron. So W is my student neuron. So at any time, this W is going to receive a force that tries to attract it to like one of M star teacher neuron, right? So you receive a force that's basically the sum over the M star teacher neuron. So you could go to any of the directions. A plus some ZT, this is just SGD noise, which you can control via some sort of martingale concentration. So how does the orthogonality help us? Is because of the following. If the teacher weights are orthogonal and the information exponent is large, for now let's assume information exponent is infinity. Okay, let's take k to be huge. Then what you can do is you can approximate this sum with a max. Okay, because the different teacher directions are orthogonal. So if you are more aligned with one of the teacher neurons, then that automatically means you're less aligned with the rest. Okay, so this means that what that entails is that if the information exponent is high enough, then basically you'll only be attracted to one teacher neuron. And that is the neuron that is closest to you at initialization. Yes?
So this equation holds for any
Mm-hmm.
k or...
Oh, this holds for any k.
Okay.
But if you look at for example, take k to be 1. So take k to be like ReLU, then this decoupling doesn't happen, right? Because now you raise this to the 0th power. So now the gradient is pointing at the linear combination of all the neurons. So you don't get any specialization. There's no decoupling. But let's say the information exponent is very high. Then the sum becomes the max. Then that means each neuron just goes to the closest teacher neuron. And then I don't have to worry about the rest. This decoupling simplifies the analysis. This is how we can handle a large width. Okay. So this is nice. And it turns out that if the information exponent is greater than 2, then you can approximate it with the max. So this is already good enough. And by the way, this is why information exponent 2 is beyond reach. So if you adopt this sort of decoupled sort of analysis, then you need information exponent to be at least 3. Okay. But why is this bad in this power law, this large condition number setting? It's because we can think of this as like a lottery ticket type of mechanism, right? So each pseudoneuron will, each pseudoneuron's fate is determined right at random initialization. It's just going to be pulled to this teacher neuron with the largest signal. But now, if the condition number is large, then the different AM have very different magnitude, right? But if you look at this max, this is the max of your initial overlap, okay, times this AM, the secondary coefficient. So if this initial overlap is going to concentrate very sharply. This is just going to be 1 over square root of D. But now if one of the AM is very large, that means all of the pseudoneuron will have a larger gradient towards this direction than all the other directions. Right? So this means that all the neurons, basically this initial overlap is not able to compensate for this discrepancy, there's a large discrepancy in the secondary weights. So all your neurons will be attracted to the same direction that have the largest AM. Okay? And in fact, in order to compensate for this, this varying secondary coefficient, you need the width of the student to be exponential. So that one of them is initialized close to a teacher neuron with small secondary coefficient. Otherwise, all of them will just ignore this direction. Okay? So this is where the exponential widths come from. It's just because we're using correlation laws, so it's kind of this lottery ticket component to it. So you only converge to the one with the largest signal, but to compensate for the signal, you need a huge number of neurons. This is also present in some of the mean field Fisher-Rao type of analysis. Okay. So how do we fix this? So we fix this so remember the assumption that we make in the training is that one, we do layer-wise training. We first train the first layer. And more importantly, we approximate the MSE loss with the correlation loss. So this means that the different student neurons do not interact. They do not communicate with each other. Like they don't really know which teacher neuron has been learned already. So the remedy turns out to be to look at actual MSE loss. Okay? And there's going to be a cheating component, which is that we use this 2 homogeneous parameterization. Okay? So this is something that originates from the ReLU literature. So now we want to train 2 layers simultaneously. And the reason is that in order to prevent all the student neuron from converging to the same teacher direction, we want to be able to somehow remove the large teacher direction from the loss after some student converge to it. Okay, so basically, there has to be some interaction between neurons. And in order to make this work, we must train 2 layers simultaneously. We must learn the direction and then learn the corresponding second layer so that afterwards, this direction can be completely removed from the loss. And now the remaining neurons can find a different direction to converge to. And so what we do is, instead of training 2 different layers, we tie the weights. Okay, so the second layer is basically the norm squared of the first layer. For ReLU, if I assume balanced initialization, if I do gradient flow, this is okay. But we're not using ReLU activation, so this is not really natural. But this this parameterization makes things work. And so with this parameterization, now we can do single phase training, because now the first layer and second layer, they're jointly optimized. Okay, you can think of it as. So there's no layer-wise training, and we don't do reinitialization or whatever. Okay. So what's happening under this parameterization is that basically you can separate the training dynamics into 2 components. One is how much you rotate, and the other is how fast the norm grows. Okay. So the rotation is going to help you find this direction of the teacher model, and then afterwards the norm should grow to the corresponding teacher weight, so you're exactly recovering it. So what we can show is that basically the rotation phase happens first. Until you align with one of the teacher neuron, it doesn't make sense for the norm to blow up. So if you start small, the norm is always going to stay small until you achieve some notion of weak recovery. After that, the norm blows up exponentially and you converge to this direction. But the magic is that after this happened, because we look at the MSE loss, after one teacher direction is fully recovered, then it is removed from the loss. So now the remaining neurons don't have to converge to that direction. Okay. So we don't have this same trouble as this correlation loss analysis where all the neurons find the biggest direction unless you have exponentially many neurons. Okay, so now there's some kind of, in the tensor literature, this is called a deflation mechanism. So you remove the components that are too big from the loss after they're learned. So here this is happening automatically because of the too homogeneous parameterization.
Unique norm?
Theta m, yes, we assume yes. So theta m have unit norm, yes.
Okay.
Yes. Is there any questions? Okay, I guess I have like 5 minutes.
Yeah, you can
Okay.
spend a few minutes.
Sounds good. So this is a sample complexity. This is the main theorem we can prove. Now with the single phase training, so there are two parts of the theorem. One is that I can tell you exactly when the mth neuron, the mth teacher neuron is learned. Okay, so this is going to give you an emergent risk curve. So the mth largest teacher neuron is going to be recovered exactly at this time. Okay, and this time is going to depend, of course, on the magnitude of the second layer weights. So if the second layer is big, that means this neuron should be recovered first. So then this Tm is small, and vice versa. Okay, time something that depends on this information exponent. Okay, and all directions can be learned with this sample complexity, which scales with this sort of the lowest the smallest second layer weights, and then this d to the k minus 1 exponent, just like the previous analysis. Okay, so basically what this is telling you is that if you ignore polylog factors here, then we need something like d to the k minus 1 samples, if you don't, and there's also some poly m star, which also depends on dimensionality. So this is sample complexity, and the number of student neuron we need is only linear in the teacher. Okay, so instead of exponential over parameterization, now basically we need at most logarithmic over parameterization, in the sense that basically it's almost a case that for each teacher neuron you only have to pay something like log d pseudo neuron, so that there's one of them that will converge. Okay, so this is the main result. And again, to compare against some of the prior works, most of them require something exponential in the condition number. Okay, so this result itself is actually agnostic to the scaling to the power law of the second layer. So this is just a sample complexity result for learning this neural network with high information exponent. But now if we assume the second layer weights of my teacher model follows a power law, then we can translate this sample complexity to a scaling description. So now under this power law with a decay coefficient minus of beta, what we can show is that now the mth teacher neuron is learned exactly at this time. Okay, you still have this d to the k like prefactor, and then there's something that scales as this m to the beta. So if m is large, you learn it at a later time. Okay, but now if you juxtapose a bunch of these emergent curves together, you can show that you'll see that the total population MSE loss is going to follow this power law decay. Okay, so there's going to be two terms here. There's going to this d to the k term is the sample or the optimization bottleneck. Okay, so if t is large, this term becomes small, and there's going to be another term that's the approximation bottleneck. Okay, so this is if the number of student neurons is small, you pay some additional price. So this, I guess, you find this very somewhat familiar because this has the same form as what Murat presented earlier for the quadratic case. Okay, and I guess the intuition is, again, it's just that we have this sort of step function-like learning curve for one direction. So now if you sum up over a bunch of them, you get this exponent. And now if your student was this small, you won't be able to learn all the teacher directions. So that incurs an additional approximation, sort of this truncation error. Okay. Right. So let me just present some experiments. So again, I think these two are typically referred to as the optimization and the approximation era. So what our theorem predicts is the following. So basically, each of the tasks is going to give you this sort of staircase type of learning curve. But as the further you go down, because then you're summing over more and more of these tasks, the smoother the scaling curve is going to become. And then we predict that you'll have like a specific exponent that's determined by this beta, this teacher parallel decay. And at some point, your pseudo network run out of capacity. So then you plateau here. Okay, so now the axis is the total compute you spend on the model. So this is something like width times the total number of SUV steps. So at some point, you run out of approximation, you run out of expressivity. So even if you increase the compute, you don't get anything. And this kind of matches with what you see in experiments. This is with a Hermite 4 activation function. Okay, so these two curves are at least qualitatively similar. The slope is slightly steeper for the empirical empirical curves because there's a truncation error of the power law because we cannot train an infinite dimensional neural network. Okay. All right, and I'll just make a quick remark on the choice of learning rate. So the analysis that we did applies to a fixed constant learning rate here. But if you want to reason about the optimal learning rate, then the idea is that because a smaller teacher direction will have smaller signal, therefore, for an SGD to work, you will need to use a smaller learning rate. Right? So that it's because the smaller the learning rate, the closer your dynamic is tracking the population, so the gradient flow. Okay, so this means that the natural learning rate schedule you should consider is something like a decaying schedule. So after you learn one direction, you should decay the learning rate a bit. And if you do this, then the exponent you get looks like this minimax optimal rate for learning this weak LP ball. So this is exponent that I guess we all find familiar. Okay, so let me skip the sketch of the analysis. And so just to conclude, so this, what I presented is basically two different analyses for learning a shallow neural network with a high information exponent activation function. So this excludes ReLU and this excludes quadratic activation. But this high information exponent together with the orthogonality of the teacher neuron allows you to use a decoupling sort of analysis. So now you can characterize how fast you learn in the visual direction and also how does the cumulative MSE loss scales. And I guess I'll just end with this edge case of information exponent 2 Murat presented earlier. So this decoupling fails, right? Just because we're raising the gradient to, we're raising this inner product to the k-1 power. It's k-1 because we take the derivative. So now if k equals 2, then basically, yeah, you will not get this sort of, this is definitely not strong enough for decoupling.